if I can find the my web browser somewhere here. It's hopefully coming through. If you have a look at our user support documentation, under our user training and outreach, user training, Pawsey training resources, you'll find this page. And if we come down here to the using supercomputers, you'll see that the slides are available in little slide sets for each topic. And there's also a link here to YouTube. And you can see my colleague Marco has recordings of all these different topics. So if you feel like at any point you've not quite grasped something, you can always come back later and check out the video again on YouTube, and also work your way through the slides if that's helpful. I think I've made 1 or 2 minor changes to the slides, but nothing very substantial. And I've just gone and compressed them all into one deck to make it easier to get through today. So as part of the training, we will be logging on to the system and actually getting to run some commands, which is really exciting. And so I think we'll leave the logistics of that as we get to probably the first exercise. So let's get into it, I guess. And if you have any questions, feel free to ask as we go. And by either putting them into chat, it's probably the best way. And if I've missed a question, please speak up. Alrighty. Too many things open, but we'll get there. Here we go. So as we go through the slides, you'll see there's these different logos attached to a lot of things. The little light bulbs is where there's a new concept. One of the things that we have as we go through the slides is I think there's a lot of new things to learn, particularly if you're relatively new to this. I think the thing to take away is that complexity is often a lot of simple things put together. And so the level of what we're doing in some ways is not that different from if you were sort of reserving a hotel for a vacation or something like that. So it's just more about just getting your head around these concepts and letting them sink in. And as I mentioned, if you don't get it all on the first pass, you can always sort of go back and deep dive later. We also have some best practices and warnings. So things that are a good idea to do and things that are not a good idea to do. And we'll also have some hands-on coding. This is less programming today and more using the command line interface, which I think you were doing a little bit of yesterday, to actually schedule work on the supercomputer and move files around. And we also have some sort of self-directed exercises that we can go through as well. User documentation is very extensive, and so it's often useful to go and look there for more details if you need it. So to get started, we'll just talk about supercomputing more broadly. What is it? Why do we need it? To, I guess, set the scene for the rest of the training. So one of the things that makes a supercomputer really special is just the sheer amount of computational power it can provide. And so there's a lot more performance on the supercomputer than, say, your laptop. And so when your laptop's not quite enough to do the science that you need to do, that's typically when you would turn to something like a supercomputer. And we have this concept of a FLOP, which stands for floating point operation. And often you'll see it as flops, and the S on the end is talking about floating point operations per second. And so a floating point operation is talking about doing like a multiply or an add, a mathematical operation, and the floating point is talking about the fact that it has a decimal in it. So it's a more complex operation than just adding whole numbers together. And so a petaflop is a quadrillion flops. And so that's one with 15 zeros. I think another way to think of it is a million billion, which is a fairly large number of operations, right? And so we measure supercomputer performance currently in petaflops. We're just starting to see the fastest supercomputers in the world are breaking into the exaflops, which is the one with 18 zeros. And so to look at what some of those systems can do, we've just decommissioned Magnus, our previous generation system, which was just over 1 petaflop. So thinking about what that would mean, if you were doing one of those calculations every second, it would take you 30,000 years to kind of get through them all, and Magnus was doing it in 1 second. And now the new system, we've hit 27 petaflops of compute power, which is very exciting. One of the things supercomputer centers do every 6 months, there's a couple of major conferences, one that takes place in Germany around June, and another that takes place in the United States in November, and we've just had the November one, is submit their performance figures to see where they stand in sort of the rankings of the supercomputers. So currently the fastest computer in the world is an exaflop system called Frontier in the States. And there's also, oops, I've lost my focus. Hang on. There's also the Fugatu system in Japan. And we've just had Photonics sort of added to that list with its full capability that we're configuring to be ready for researchers at the start of next year. And it came in at number 15. So you'll hopefully be logging on to the 15th largest supercomputer in the world later this morning or this afternoon, depending on where you are, which I think is really cool. So the scale of the supercomputer is useful for ranking, but one of the more important things is what it's actually used for. And there's a really wide variety of different use cases that we see across the researchers that use the facilities at Pawsey. I think we have several hundred projects, a couple of thousand users, and we have use cases in health, looking at sort of genetic studies and studying how molecules interact in sort of the human body to get better understandings of different types of diseases and illnesses. In astronomy, we support 2 functioning radio telescopes at Pawsey, the ASCAP radio telescope, which is these large radio dishes that are good for studying high frequency radio waves as they come in from the universe and turning them into pictures so we can study them, as well as the Murchison Wide Field Array, or the MWA telescope, which uses these dipoles, which you can see here in this picture, which are more suited to receiving lower frequency radio waves. And both of these telescopes are located out in the West Australian desert, and the signals are sent over fibre optic to the Pawsey, where some of the computations are run to turn them into those images that are actually useful for producing science. We also have a lot of studies in energy, from looking at new chemicals to have better energy storage in batteries, doing computational fluid dynamics to understand how the ocean can affect oil platforms. We have agriculture, so how to get a better understanding of pests that might be feeding or adversely affecting crops. Looking at the genetics of crops to understand how we can maximize the output and make them drought tolerant and other things. And finally, we've also had great modeling of Perth's aquifers to see what can be done to make maximal use out of the aquifers and ensuring that the water there remains safe for drinking. So to turn a little bit to the hardware of what an supercomputer actually looks like, I think we saw a couple of slides back, the Photonics supercomputer, you can see it's got all these cabinets in it. And each of these cabinets is stuffed full of circuit boards and processors. So a modern supercomputer is made up of lots and lots of processors, which sort of present themselves as actual individual computers. So a better way to think of a supercomputer is not as one big computer, but rather as thousands of computers that are all connected together. And the important thing is actually less the computers and more the connection of those computers together. And by having all of the nodes, computers of a supercomputer able to talk to each other really quickly, it allows them to collaboratively work on these large scientific computations to get the results done in a fast amount of time. So here we see the major parts of a supercomputer, if we can break it down conceptually. In the center here, I guess you have the main heart of the supercomputer, the compute nodes. And so as I mentioned, each node is an individual computer that are all connected together. And then in order to make use of them, we have a scheduler, which schedules when you get to run your jobs on the system. It's really important that because the supercomputer costs quite a lot of money, we want to have jobs running at night, we want to have jobs running on the weekend. So we want to have it completely and utterly packed full of work for it to do. And so everyone puts their jobs into the queue, and then when there's time available, the job runs out on the compute nodes. Equally important to the compute nodes, which are running the programs, is the high performance storage, because the programs will be working on data, input configuration parameters or data sets, as well as temporary data products that we're producing along the way, our final results. And it's just really critical with sort of thousands of these compute nodes all running that we have this really high bandwidth connection to a very large, fast, high performance storage, so that the nodes are not held up waiting on information. So we have this high performance storage that's attached very closely to the compute nodes. So then we have what we need to do the compute. How do we actually get in there and do it? We have the login nodes. And so these are just computers that we're logging into. That from there we can manage what's happening on the supercomputer. And so it's one of the really important things to understand is that the login nodes are not the supercomputer in a sense. They're where you go to launch your work onto the compute nodes, which are separate. And similar to the compute nodes on the other side here, we have data movement nodes. And so these are very similar to the login nodes, the difference being that they have very high bandwidth connections, both to the high performance storage and out to the rest of the Pawsey Center and the outside world. So this is where all the large data sets should be moved in. It's really important not to do your data movement through the login nodes, because that's where everyone's sort of logging on and trying to work with the supercomputer, and you don't want that saturated with data. And so we'll talk about that, and what it actually looks like as we go through. So to talk a little bit more about the compute nodes, in terms of the individual performance, they're quite similar to a very high-end workstation. So the current nodes in Photonics have 2 processors with 64 cores each, or a total of 128 cores. And the performance is coming from all of those nodes working together on problems. And so because of that, it's important that the programs that you're running are able to sort of do work at the same time on lots of different computers. And so there's a lot of parallel APIs or libraries or pieces of software that you can use, which I'll be talking about a little later, to allow them to communicate with each other as they're working on your problems. Wherever possible within the supercomputer, we've kind of maximized the performance of the communication between the central processing unit, or the CPUs, and the memory, and the high performance storage, to make sure that communication isn't a bottleneck. So, to talk a little bit about the interconnect. So as I mentioned, all of these compute nodes, which are those individual computers that make up the supercomputer, are connected via a very fast network. And you can see here, this picture is from our last system, which is lots and lots of cables. You can see the green fiber optic cables, which are used for the longer transfers, and these different colored cables here is copper, which is used for some of the shorter hops. And you've got this very close networking of all the nodes to all the other nodes. And by having these really close connections, it means that the communication can happen really quickly. And this is what, I guess, separates the supercomputer from something like the internet. You might have heard of things like folding at home or SETI at home, where you can kind of work on a problem collaboratively by using lots of laptops and home computers around the world, all working together on the same problem. That works well for some problems where you can easily cut them up into little pieces, and the communication between them matters less. But there's other problems that you might have in science where you need constant communication between all of the parts of the problem, and that's where you really need the supercomputer to make that happen in a meaningful amount of time. So one of the really important things about making use of the supercomputer is parallelism. So parallelism is where you are doing things at the same time. It's kind of opposed to, we talk about serial processing, where you sort of do things sequentially, one after the other. And so it's what you kind of see here on the right. So we're doing the first thing, and then we're doing the next thing, and then we're doing the next thing. For parallelism, we're doing it all at the same time on these different compute nodes. And that's how we actually make things run faster. So I've worked with researchers who have had problems that might take weeks or months to run. And then we sit down and try and figure out ways that we can run things at the same time to make use of the supercomputer, and then we can get that done in days or months. No, sorry, days or weeks, depending on the scale of the problem. So the high performance storage here, it's fast storage that can be thought of as inside the supercomputer. Sometimes it's physically sitting nearby, and then cables are connecting it, so it's so it appears to be in the supercomputer. And it's really useful for analyzing extremely large data sets. So we talked a little bit about petaflops. That was one peta being one with 15 zeros after it. Our high performance storage has petabytes. So if you think about, say, a terabyte portable USB hard drive or something like that, then a petabyte, it would be 1,000 of them. So we've got many petabytes of working storage in our high performance storage. And one of the important things is that it's global. So all of the compute nodes can see the same high performance storage. So if you're writing a file from one compute node to a location, and you're writing it on a different compute node, it's the same place. So you've just got that global access. And if you're working with very large data sets, they will fit. Some supercomputers also have local node storage, where there's storage on the node, which can be useful in some use cases. And for photonics, we will have that on our GPU nodes. So that, I guess, is a general introduction to supercomputing. So hopefully we have a better idea of the different parts of a supercomputer and some of the things that make them super. I haven't seen any questions come through so far, but if you have any, now is probably a good time. I'll take a stunned silence that I should continue. So in this next section, we're looking a little bit about the supercomputers that we have at Pawsey, just to provide some context. So we have Photonics, which is our new system. And as I mentioned, it had that fast file system, so 15 petabyte Lustre file system that's connected with 100 gigabits per second to Photonics. And then out to the rest of the center, we have a 100 gigabit connection, which connects Photonics to the other systems. We do have a couple of other high performance computing systems at Pawsey. There's Topaz, which was our GPU computing system that was part of our last generation of supercomputers, and it's still around because we're bringing up the GPU portion of Photonics to be available next year, and so we're expecting to decommission Topaz a few months into next year. There's also a couple of systems that support those radio telescopes I was talking about earlier, such as the ASCAP ingest nodes and the Garawala system. We also have some different types of storage that are less closely connected to the supercomputer. They still have a very good connection through this network, and that includes the Acacia object storage, which I gather we'll be covering in more detail through the training later in the week, as well as our tape storage system, which remains a very energy efficient way to store data in the very long term. So in terms of what you can log into today, this is the current phase of Photonics that's available. We're currently in the process of configuring the final phase, which includes a significant number of more compute nodes, as well as some GPU nodes. So for those of you that are not familiar with GPUs, many years ago, computers just had the one processor, a central processing unit, or CPU, and it was found that the operations that were being used to calculate what was being displayed on the screen was somewhat different from the main work that the CPU was doing, and it was advantageous to have a different type of processor for it, a graphics processing unit, to focus on what was going up on the screen and having the CPU doing most of the work running the programs. And over time, these GPUs, or graphics processing units, got more and more flexible in what they could do, and it turned out that calculating what is the pixels on a screen is not that different from calculating a lot of scientific algorithms. And so modern GPUs are very applicable to a wide range of scientific algorithms, and so they can be used to accelerate codes. So what we see currently on Photonics when we log in, we have a number of login nodes. We also have those data mover nodes I was talking about. We have some visualization nodes that are accessed separately through a different system. We have our compute nodes, 504 of them with 128 cores currently, and 8 high memory nodes, which have a terabyte of memory on them, which can be useful in cases where you've got codes that can't communicate beyond more than one node, but need a lot of memory. It's a useful place for those kind of codes to run. We also have a number of file systems that are globally accessible, so you can access them from all of the compute nodes and the login nodes, which I'll be talking about in more detail as we go through. Our Slingshot interconnect, which is connecting everything together, our network out to the rest of the center and the outside world, as well as the Acacia object storage. And we'll be covering all of this in a lot more detail as we go through. So I talked a little bit about the importance of the interconnect in connecting the computer together. And what you see here is a diagram of the interconnect on Photonics. It's a little bit simplified, but what you can see is these little circles here are the nodes of the supercomputer, and several nodes are connected to these routers. And you'll notice that the routers have a number of links. So they're in these groups, and every router within a group is connected by these blue lines or these blue networks. And then each group of routers is connected to every other group. And so what that means is if you want to get from any node to any node, for some subsections, so within a group, you've got a direct connection via the blue line. For other nodes, you may have a direct connection via the black connections. But from any node to any node, you will always be able to do a hop across blue, a hop across the black, and then another hop across the blue. So at most, it's going to take 3 hops. And so this is an improvement on Magnus, which was a 5-hop topology. And by minimizing these number of hops that the communication needs to take, it means that the latency of the communication is removed. So the messages get there quicker. And this is really important if you have a big simulation or a software that's running on the system that is communicating frequently. You don't want your nodes sitting there waiting for messages to arrive. You want them having the information they need to be doing active compute. So having a low latency network is really important. In terms of the actual architecture, so coming back to this diagram of things connecting together, down in the bottom left there, each cabinet of Photonics, so those cabinets are these large sort of fridge-sized cabinets you're putting these 8 chassis into, and each chassis has these 8 compute blades that have 4 nodes on them, and all of these are just packed tightly into the supercomputer and connected into those switches that connect all the nodes together. To go into a little bit more detail around the actual processes themselves, what we see here is a picture of the layout of the processor. This is a Zen 3 based processor, if you're familiar with the different architectures of CPUs. And what that means is that the chip has a number of these chiplets on it. So you can see here, we have in the light blue our cores. So our cores is what is running a program. And we have 8 of those cores per chiplet, and then we have 8 chiplets for a total of 64 cores per processor. And then we have 2 processors on a node for a total of 128 cores. So one of the interesting things is that these little chiplets have a shared cache where when they're reading in data, there's a copy of that data sitting there. So if another core happens to access the same data, it's already sort of on the chip sitting in the cache, which makes it a bit quicker. And because of this chiplet architecture, we recommend if you are running a parallel program with lots of processors or threads, then multiples of 8 are your friend on this particular architecture because it's likely to be the sweet spot for running things. So if you're wondering sort of how many threads or processes to run when you're scheduling your work and you're wanting to do some sort of scalability studies, rather than running for sort of 1 thread, 2 threads, 3 threads, would recommend trying maybe 8 threads or processes, 16 threads or processes, and see how it goes. So that brings us to logging in. So we can actually have a go at getting onto the system. Are there any questions so far? I'll take silence as a no. Oops. I don't see any more chats. Are we all comfortable with the terminology I've been using? When I'm talking about processes and threads, is anyone lost or confused? I'll take silence as a no. But I encourage you to ask questions. If there's anything I'm covering, definitely don't be afraid to ask questions. It's really important.
Chris, we have one question in the chat.
Yes.
From Luke.
Yes.
Saying, do you have any examples of calculations that GPUs are better than CPUs?
Yes. So for my PhD, I was working on radio astronomy correlation, which is where you've got different radio signals coming into those different antennas that we kind of saw in that picture. And what needs to be done is all of those signals need to be multiplied together following a fast Fourier transform. And so fast Fourier transforms run really well on GPUs, and just doing bulk multiplication of values near each other, it's really good at. So if you think about it, a GPU has come about because it needs to figure out all the pixels on a screen. And when you think about calculating the color of a pixel, it's not particularly complicated, but there's a lot of them. And so the architecture is really good at running lots and lots of simple threads at the same time, working on data that's very close to each other. So if you have big arrays of data and you kind of need to do the same thing to every element of the array, that's the kind of things that GPUs are good at. Whereas if you think about a CPU, it has fewer cores that are more powerful. And so it's better at running more complex processes and programs that have more variables attached to them, that require more in-depth branching. So if you're doing sort of like tree searches and things like that, then I'd say it's likely that a CPU may be better at that kind of work. And so just when you do GPU programming, what you'll typically have is you'll be using your CPU as a host processor to control the program logic and doing those sort of heavyweight tasks that require a lot of variables and a lot of branching and a lot of logic. And then offloading sort of simple work where you just need to do a lot of it on a lot of different elements. So matrix operations, working on arrays, signal and image processing, or running simulations where you don't have too many variables and but you've got lots of elements and very large data sets to work on.
Great. Thanks, Chris. That's very helpful. We have a couple of other questions in the chat if you have a bit of time for them.
Yeah, definitely. This is really important.
So we have another one from Yayu. I hope I said your name okay. So what's the difference between processors, nodes, cores, and threads in the supercomputer?
That is an excellent question. So there's, I guess, two categories of things in all of that we should be really thinking about. One of them is the hardware. So that's the actual circuitry that's doing the work and running our programs. And then the other is the actual programs themselves. So in terms of the actual hardware and circuitry, we have our supercomputer, which is made up of our nodes. So each node is an individual computer that's part of that network. And on the node, the computer that makes up the node, you have the actual processor. And the nodes that we have on Sotonix actually have two of these processors. Sometimes these are called sockets because the word processor gets used a bit interchangeably with some of the other terms I'm about to go into, and whereas a socket is something that physically the processor kind of goes into. So that's in some ways an easier term to work with. And so we've got two sockets per node on Sotonix. And then within that socket, we have this diagram here. So that's where we then have these 64 cores. And a core is what a processor used to be. So if we go back 20, 30 years, computers used to just look like one of these blue things for a processor. And what we used to do was increase the clock speed of how quickly the processor could run through the program. And so it started off in the megahertz, then went up to the gigahertz. And then we hit this point where, unfortunately, the power consumption of a processor is not linear with how quickly it runs. It actually starts using more and more power as it runs faster. And we kind of hit what's called a power wall, where an individual processor, we can't run it any faster because it consumes too much energy and gets too hot. So because of that, we then started using parallelism. So that's why we have all these lots of little blue things, all these cores. It's we have multiple sort of these processing elements on a single processor, and these are called cores. And so if you just take a program that you've written, just an average serial program that you might have, and you run it, it's only going to be able to run on one of these blue things, one of these cores, because it doesn't have any parallelism in it. So that's where we start to switch our terminology. So I've been talking about the hardware so far. Now let's think about the software. So we have a program. So we've got a program is a lot of commands that we've written that we want the computer to run and go through. And so we can have a serial program, and when that program is running on the computer, it will be running on one of these cores, on these blue cores. And the act of it running is called a process. And so a process is a program that's running on one of these cores, and it has all the variables and access to the variables of the program that's running. And that is one process. So one of the ways that you can make use of parallelism is to have multiple processes. So you write a program that is okay with having multiple versions of itself running, and it can talk to each other. And so you say, okay, well, I'm this version of the program. I'm going to do this bit of the problem. You're that version of the program. You're going to do that bit of the problem. And so you have multiple processes running on each of these cores. And then there's also a concept called threading. And threading is where you do something a little bit similar in that you have multiple instances of the program running. So it's running the commands of the program at the same time in that parallelism, but threads are within a process. They can see all the variables. And that's only possible within one processor. And so what you'll find is that if you use threading, you are able to have multiple threads that are all running and able to share memory, so they can just share variables with each other. And you might have lots of threads running on all these cores, and they're working through the problem. They're doing their bit of the problem. They're communicating by writing to their shared variables as they're going through. And but you are limited to one processor. So once you get to 128 threads or so, or the number of cores that we have, you're not going to see, if you start putting more threads, we don't have any cores for them to go on. And so that's why we have the other type of parallelism, which is the process-based parallelism, because then potentially we can have processes running on other nodes of the supercomputer, and then they communicate over the network, but they can't see each other's variables. They have to sort of pass messages between each other. So I'm going to use this terminology as we go through. And so I appreciate that's probably a lot to take in all at once. But to kind of run that through one more time, we have on the hardware side, we have the processors or sockets, which are the sort of physical chips that are plugging into the motherboard. Those sockets have cores on them, which are what actually run your programs. Your programs, when they're running, are called a process. And a process may have multiple threads of execution in them that can sort of share variables and work their way through. Yeah, and so you'll come across these terms if you are using a piece of software or writing a piece of software that can make use of parallelism to sort of have multiple threads of execution or multiple processes working on a problem together.
Sounds good. Thanks, Chris. We do have a couple more questions. I don't know how you're feeling about time. Would you?
I think we should definitely get through them, and I might try and be a bit brief with my responses.
Sounds good. So we've got a question from Abraham that's just asking about the communication latency you mentioned before. So can you just explain what that means exactly? Is it something?
Yeah. So latency, if you think about the compute nodes as people, and they were sort of working on a problem together, you might get to a bit of your problem and you're like, oh, I need some information from the other person that's working on this. I can't do anything until I get that information. So I'll send off a message saying, hey, could you send me this information because I need it? And you wait, right? Because it's going to take time for that message to get to that person. And then it's going to take time for that message to get back. So ignoring how long it takes for the person to sort of turn it around and get back to you, there's just the time it takes for the message to get to them and the time it takes for the message to get back, and that's latency. And so you want that to be really quick, so you're not waiting for that message to be in transit.
Great, thank you. And so next question, we have one of our interns, Brittany, will be working on Nimbus. And so she's wondering what the differences are between a system like Nimbus and Photonics.
Yes, so Nimbus does not have that all-to-all network. So you're kind of more focused on individual nodes, I guess. And it also doesn't have a, what's the word? Sort of an operating system that is there set up for you. And so you're kind of responsible for being a little bit of a system administrator. So you kind of create your instance, and then you have to sort of set up your user accounts and add users. And so there's a little bit more work in terms of having the environment. You're very much responsible for setting up the environment. The advantage of that is you can do whatever you like with it. So you're not constrained by the particular operating system that we happen to run on the supercomputer, for example. So for problems that fit on the cloud, it's very flexible and a really good approach.
Wonderful, thanks. And last question that I can see for now is from Helen. So she asks if the supercomputers at Pawsey allow for basically regular standard Python programming, and whether that means we need things like distributed approaches like PySpark for Python.
Okay, so yes, for Python programming, we have, there's a lot of ways that you can make use of the system. There's certainly nothing wrong if I come back to, there's a slide. This parallelism slide. This parallelism doesn't necessarily need communication. There is the concept of things like parameter sweeps or work where you just have a lot of work to get through, and on a single computer it's going to take years, and then you put it on the supercomputer and you've got lots of computers doing it at the same time. They don't necessarily need to communicate, but because you've got you know, 1,000 very powerful computers, you can get all that work done very quickly, and that's still a useful use of the supercomputer in terms of reducing your time to science. In terms of Python, one thing I would say is that it is an interpreted language. And so there's interpreted languages are where the computer is interpreting the program as it's running it, versus a compiled language where you compile it up and convert it into machine code beforehand, and then when you run it, it runs a lot quicker. But there are libraries in Python that are compiled. So there's NumPy and SciPy, which are very performant because they're actually compiled. And so if you're using those numerical libraries to do your numerical work, then yes, you could definitely be using Python on the system. But just if you're just writing your code in raw Python to do the work and not using those compiled numerical libraries, it might be something like 600 times slower. So it's really important to make sure that you are writing efficient code first, because you might not even need a supercomputer. That times 600 might means like, oh, I could just do that on my laptop. So it's definitely worth being aware of what your code is doing. And there's also some things like, I think it's MPI for Pi, and other distributed packages as well for parallelism using Python. So I think Python is a very useful tool, but there is the danger of doing things inefficiently if you don't know what you're doing. So it's just something to be aware of.
Great, thank you. I think they're all the questions I can see for now.
Excellent. I will keep going because otherwise we will definitely run out of time. But thank you for the questions. I really appreciate it. So module 2, logging in. So how do we actually make use of the supercomputer? So we have this concept, remote access. So we distributed around Australia and do lots of different places, but we all want to make use of the supercomputer, which is sitting in our machine room. And so we're going to remotely access over the internet to log into it. And we're going to be using a command line interface. So this is a interface that hopefully you would have had some exposure to yesterday. So you type commands and then you get your responses back via text or through writing to files. As I mentioned, we'll be using these login nodes. And so it's really important that we're using the login nodes for, I guess, administrative type work on the system. So what we don't want to do is jump onto the login nodes and run our sort of complex or heavy computational workloads directly on the login node, because there will be other users using it and they're not going to be happy, and you'll probably get a grumpy email from one of our system administrators asking you telling you that they've killed your processes that you've been running, and please don't do it again. So what the login nodes are good for are sort of getting a feel for the different parts of the supercomputer, organizing your directories and files, setting up your analysis and simulations, and then sort of submitting your jobs to the scheduler and then having a look at how they're going. As well as not running computational programs, also definitely don't transfer large files through the login nodes. Make sure we're using the data mover nodes, and we'll be going into that a little later. So what we're going to try now is to log into Cytonix. And Emily, I understand you have the credentials for everyone?
Yes, so everyone, the credentials, they're going to be in the Google Drive link that you should all have access to. So we've put a new file in there this morning called Intern Training Accounts. I will put the link in the chat as well so that everyone has it. There we go. There we are. And so what we need is we need everyone basically to just pick a login username and password and put your name next to it so that we know that it's taken and we don't have people doubling up on the same account.
I will be using number 40, so please don't take that one. So what you should see there is a list of usernames, which all start with COU and then 3 numbers. And then in the next column, you'll see the password, which will just be a number of words, dictionary words sort of concatenated together. After that, there's also some keys. We won't be using those this morning. They're for accessing Acacia, which is probably a little much for one day. So what you'll be wanting to look for is that username, COU, number, and the password. And I might give us a little bit of time to have a look at that before I move on to the next bit.
Are we view only on that document?
So yes, sorry, the first time I uploaded it, yes, but if you refresh it, everyone should now have edit access.
So the other thing you'll need is an SSH client. So if you're on an Apple or Linux, it should just a case of opening up a terminal window. If you are on Windows, we currently recommend using a program called MobaXterm, which you can just find by Googling MobaXterm. And there's a download there, which comes in, I think, a portable installer. So if you have a somewhat locked down laptop, hopefully it will still run. And if you're stuck, please let us know.
And I think Windows users, if you were using the Windows subsystem for Linux yesterday, that, correct me if I'm wrong, Chris, but that should also be okay for SSH
yep,
today.
Definitely. And there's also another program called Putty that I know some people like to use as well. Hopefully my client has decided to stop working, which is interesting. There we go. How's everyone going? Claiming a username and opening a terminal. Is that readable for everyone?
Yeah, looks
Cool.
good to me.
Alrighty. So what we're going to do to log into Stonix is we're going to be making use of an SSH client. So this is going to run the SSH command, and I'm going to specify my username. So here you'd be using the number that you've claimed from that that file. I'm going to put the @ symbol in there, and then I'm going to put in the host name to the Setonix login nodes, which is setonix.pawsey.org.au. And so this is telling SSH that it wants to log into this server using this username. So what you should see is a notice from the system, and then it's asking for a password. Some clients will not show up anything while you're typing in a password, so you'll not necessarily see anything as you're typing, but it is going in. And so you want to type those words, that is the password in that second column. And that will get you into the system. If you are getting it wrong, slow down. If you get your password wrong too many times, the system will assume that you're trying to guess people's passwords and will blacklist your IP, which will get you locked out. If that happens, then the best thing to do is to send a help desk ticket to our help desk saying, hey, I've accidentally got blacklisted. It's no longer allowing me to attempt passwords. Can you investigate and have a look at removing me from the blacklist? And what we'll see when you've successfully logged in is our message of the day, which is worth having a look through. And you'll see that I've landed on Setonix 03. Another way to tell is by running the hostname command, which is always good for finding out what the name of the computer you're actually logged into is. So you can see here it's Setonix-03. Depending on where the round robin landed you, you may have ended up on Setonix-01 or Setonix-02. So if I use the users command, you can see there's a lot of people logged into the system and using it. And I can see a number of you have successfully logged in here, which is great. All right, I will keep moving. So we'll get back to the slides. If you're having trouble, please definitely let us know in the chat. Okay. I think I've covered this. So there's things that you could have a go at. So I think I've covered off the first one. If you remember back to yesterday, hopefully they may have covered the pwd command, which will tell you your current working directory, and the ls command, which will show you what's in a directory. And you also notice there's these environment variables, and hopefully you'll be able to use the echo command to echo those out and see what they contain. Again, I'll give a minute or two to have a look at that. So our present working directory is our home directory, /home and then /our username. Currently, there's not much in here. The home variable contains the path to our home directory. I've got a MyScratch, which we'll be looking at in a little while, and a MySoftware. Similarly, as a path to a location on the file system. So if you ever forget your password, there's a web form that allows you to reset it. I've already talked a little bit about the blacklisting. And another thing to definitely remember is that typically we have maintenance on the first Tuesday of a month. So if you ever go to log in and you can't find the system, it's definitely worth just double checking whether it's the first Tuesday of a month or a maintenance day, and you can check our maintenance and incidents page, which might save you a bit of time before sending in an email to our help desk. So there is also a few best practices and things not to do. You can use SSH keys to improve the security of logging in, which I'll talk about briefly in a moment. You should not share your account. We've made it really easy for project leaders to invite other people to the project, which they can do through our web portal. So please don't share accounts. It's important to us to have a good idea of who's using the system, both from a security perspective and also for reporting to our funding agencies of how many people we're supporting. And you should also not provide your password to anyone, not even in help desk tickets. We will never need to know your password. You can use what's called SSH key authentication to improve the security of your account, which I'll skip over the demo, but basically you can use these commands to create a encrypted key and then have a sort of public version of that key that you then use to, when you're logging in with SSH, as you can see here, you use this -i to provide the location of your private key when you're logging in, and the system will check that against your public key that you've sort of added to your account on the system as a second layer of authentication to verify that it's you. We do not recommend using passwordless keys, because then if someone gets your key, they can simply get in. We recommend using a key with a passphrase to make sure that someone else can't use your key. So occasionally you may want to use a graphical interface, and so depending on what you've used to log in, you may be able to do what's called X forwarding or X11 forwarding. So for Linux and Mac, there's -X's and -Y's that you can specify to do that. And then when you run your graphical interface, it will show up on your desktop. However, it's not the greatest, particularly if you're over the internet, because it's having to sort of transmit all that information constantly. And so if you are looking to use the system in that way, we have a remote visualization service, which uses technologies that are slightly better for that purpose. So that brings us to module 3, file systems. Do we have any further questions? We'll keep going then. How are we going for time? Okay. So a file system is the way that we store files on the computer. So you may be familiar with directories and then files in those directories. Sometimes directories can be called folders. And a file system is what is holding the information of these directories and files. There's different names for them. So on Linux, ext4 is a common one. There's different file systems for Apple and Windows systems. And as I mentioned, we have that high performance storage that actually has a number of file systems on them. And the important thing about these file systems is that they're specialized and should be used for particular purposes. And we have policies for each of those file systems. And a reason for that is that when you're actually specifying the design of a file system, you can make choices as to what kind of performance it has and how much storage it has. and how that file system is used. And we only want to, I guess, spend money on particular aspects of that performance and storage if it's needed for a use case and not wasted on others. And so it's really important to use the right file system for the right purpose. So some important ones to have an understanding of were the ones that we just saw in that demo, in that exercise. And so there's our working data, which should live on the Scratch file system. So this is the big data sets that our programs that are running on the computer are making use of, should live in Scratch. In order to keep Scratch free, it does have a purge policy, so that data can get deleted after 30 days after you've accessed it. And so for that reason, we also have a software file system for storing software, the programs that you're making use of when you're running on the supercomputer. For longer term storage of actual scientific data, we have the Acacia object storage system, which is not quite a file system, but a place to store your files. And we'll be covering that separately later in the week, I believe. And then finally, there's the home file system, which you should use as little as possible, but there's certain configuration files that the system expects to be located there. We also have a couple of radio astronomy specific file systems that are mounted on the Garawala supercomputer and a couple of other parts of our infrastructure. So, as I mentioned, the Scratch file system should just be used as a temporary workspace. The idea being you stage your files up onto the Scratch file system, you make use of them with jobs on the system, and then you take your output and you put it somewhere else. And this is really important because it's a shared file system, and we want to make sure that there's plenty of available space and performance for other jobs running on the system. We do have a 15 petabyte total capacity, and we have some limits of a petabyte and 1 million files per user, just to make sure that we have the availability of the file system and the performance of the file system available for everyone. Your directory on Scratch, you can find in that My Scratch environment variable, and it has this layout of /scratch/ your project ID. So you will notice from the example that all of the course accounts was in I think a courses project, and then the actual username. And so for these course accounts, it's that COU number username. As I mentioned, files on Scratch are purged after 30 days. Please do not, under any circumstances, do something like put your PhD thesis, the only copy of your PhD thesis, on Scratch. It is not the place for it. We have had one unfortunate incident where that did get deleted, so please don't be that person. Make sure for things that are really important, you have lots of copies of it in lots of places that are geographically separated around the world. It's really much just there for actively using on the system. We also have some commonly used data sets. So for certain domains where there's gold standard data sets that get used for reference, rather than everyone having the same copy of that data set, we provide copies of it in /scratch/references. Currently, there's some climate modeling and some bioinformatics data sets sitting there that may be useful, and so definitely worth being aware of. So the object storage, Acacia, as I mentioned, we'll be talking about it more later in the week, and it is a place where you can use what's called an S3 interface to store and retrieve files, and also share your files with others across the internet. So it's useful for storing and sharing data. It is not recommended to be used as a place to work with your data. So the idea is that you have your data on Scratch, you work with it through your programs running on the supercomputer, reading and writing data, And then when you are ready to store it, if you need to use it again later, you sort of archive it and put it on the Acacia object storage. And then when you need it, you pull it off again and sort of start working with it again. The software file system is where you can install your software. We currently have quota limits of 256 gigabytes per project and 100,000 files per user, but we are investigating increasing that number of files because we're finding for some particularly complex pieces of software, it's not quite enough. And this is organized in a similar way to Scratch, except that there's an extra directory in there, projects, because we have some other software that sits on that file system, such as the system software stack. So it's /software/projects, then your project ID, and then your username. And it's there in that My Software Environment variable to make it easier. For home, it should just be used for configuration files because it's not a very performance system. And it's also worth noting that sometimes if you're running certain pieces of software like profilers or other things that make use of the system, they sometimes store things in hidden directories that start with a dot in your home directory. And so if you're finding you've suddenly hit the limit of your home directory, it's worth going and having a look, and you might find that there's a dot file directory there that has a lot of data in it that you don't actually need because it's temporary. So that's just something to be aware of. So you can access your home directory in home/username. You can use the $home environment variable, or the tilde symbol will also be a shortcut to that as well, which can be helpful. One thing we definitely don't recommend doing is one of the things that is stored in your home file system is this .bashrc file or other files that are executed when you log in. And it can be very tempting if you always make use of a particular piece of software to say, well, I would just want to automatically load that piece of software when I log on to the system. So I'm going to put it in my bashrc file. And the problem with that is that it's not portable. So if you want someone else to help you, or you want to share your computational workflow with others, they won't have the same bashrc file as you. They won't have those same startup scripts. So we recommend just leaving the .bashrc as default as possible, particularly for loading software environments. And instead put all of that in your job scripts. So that way, when you provide your batch scripts to other people, all of the configuration for them in terms of setting up the environment is in that script and portable, and not sitting in your login script. Alrighty, so that brings us to monitoring our file system usage. So how do we know how much of the file system we're using? And so there's a couple of commands that we'll look at. There's quota, Pawsey account balance, and LFS quota. So feel free to follow along as we go through. So we can type quota-s. And we can see here, this is providing information on our usage of the /home file system. You can see here we have a quota of that one gigabyte, or 1024 megabytes. And currently there's 112 kilobytes that are being used. And we have 31 files out of our 10,000 file quota sitting there. We can then do a Pawsey account balance. So this is a sort of a custom script that we've provided for finding out about your usage of the system, and with a -s. And that will provide you with information on your usage of your allocation on the system, which we'll talk about a little later, as well as your usage of the file system. So you can see here, we're talking about how many gigabytes out of the terabytes that we have available on Scratch, and the usage of software. We've used 5 gigabytes out of our 256 gigabytes. There's also the LFS command. So this is short for the Lustre file system that Scratch and software use. And so you can do an LFS quota with a -H to make it more readable. So that's responsible for putting things like Ks and Ms instead of just big numbers that are hard to interpret. And then you can do that at a -user level, -u, and then your username on /Scratch. And it will show you how much you've used on your Scratch and your files. And you can also do that at a group level as well. So you can see we are in the courses 01 group here. So if I change this to be a -G for group, and we'll look for the courses 01 group, you can see how our group quotas are being used there as well. Cool. It's a good idea to just keep an eye on your usage of the file system, because once you hit the limit, you'll find you won't be able to create new files, and you don't particularly want that to happen in the middle of a very large job that's using up your allocation. You'd ideally know that you're getting close to hitting it and taking action to delete unneeded files, or moving files off the system, perhaps into Acacia or back to your own systems to make sure you're well below those quotas. Cool. Were there any questions on that so far? All right, I see there's quite a few questions from the last exercise. So in terms of using a login that's been used previously, you can, although things that you run would be used against projects that you've been allocated. So I think for these exercises, it's probably easier to just use the COU accounts, but feel free to use your own, particularly if you've got an active project that you're happy to spend allocation out of, because you probably won't use up much of it. Yes, the password is the two-word password. Yep, I think Emily answered the question of using Control-C if you make a typo. I believe you will be sorted out with accounts for your projects. I suspect it will be in a sort of case-by-case basis as to like what's the best approach, because I suspect every intern project is a little bit different. Some researchers will already have projects that they want to add you to because it'll be easier because you've got to sort of access the same files. Other projects might not have an allocation on a particular system that's needed. So definitely that's, if you're finding you're needing something, please speak up and we'll try and sort something out. And yeah, have those conversations.
Yeah, I guess I can just jump in there quickly, Chris. So everyone should already have their Pawsey accounts related to their projects, and you can chat with your supervisors about what system exactly that's on. Not everyone will be working on Cetonix. Some of you will be working on Topaz, I believe. Some people are on Nimbus. So yeah, that's something to check with your supervisors and with the emails you've already received.
Thanks, Emily. So let's keep moving. So we now can log in and have a little bit of look around, which is fantastic. And now how do we actually get data to the system. So we might have a data set that we're wanting to actually start working on. How do we get it there? So this is where we have those data mover nodes. So as I mentioned, they have those high bandwidth connections, and that's what we should be using to move the data in and out of the system without overloading the login nodes. And this is sort of a conceptual diagram of how to think about how you can move the data. There's actually two of these, one for pulling and one for pushing. So we're out here in the world. We have the option of going through Acacia, which we'll find out about later in the week, but we're going to be focused on this path here. This is kind of the path that we're taking here. We're coming. It's worth noting that there are.
Sorry, Chris.
Yes.
I think you just for the last 5 seconds or so, you just froze.
Oh, that's no good. Excellent. I guess what I was saying in the last 5 seconds was we're going to be looking at this path here. So from the world through the data mover nodes onto Scratch. Or other file systems on the system. So in terms of access to the data mover nodes, we have that remote access using SSH in a very similar way to the login nodes, and there's programs that can use that secure connection to make those data transfers. It's worth noting that there are firewalls. So some institutions may block your SSH connections. Typically, most institutions will let you SSH out, and so you shouldn't have any problems around that. But one thing that we do find is a problem is sometimes when you're using licensed software, the software that's running on the supercomputer might need to connect back to a licensed server that's running at your institution, and it hits the institutional firewall. So if that's the case, then you need to provide your institutional IT information on what IP addresses to kind of let that traffic through, so it can connect back to your licensed servers. But if you hit that problem, definitely open up a help desk ticket, and we'll walk you through it. We also have a petition in the scheduler, which I'll be talking about a little later. So you can actually run dedicated jobs that are on the supercomputer for transferring data. So let's have a little bit of a look at how to transfer some files using SCP. So SCP is, I guess, the most basic tool that you can use for transferring data. There's also a slightly more sophisticated rsync, which will do things like if your transfer is broken halfway through, it'll sort of start from where it finished and continue, which can be quite useful. And there's also a number of GUI clients that you can use as well. That can be quite helpful. Happily, I've been disconnected, so that makes it easy. But if you are still logged in, note that the commands I'm about to type are not on Sotonix. I'm typing them on my local terminal. You'll find if you are not actively using the system, you will get kicked off occasionally. And this is necessary because otherwise, potentially, if people get disconnected, their login sessions will just sit there indefinitely because the login nodes stay up for a long period of time. So what I'm going to do is I'm just going to create a file. So I'm going to echo text to a file. And if I do an ls, hopefully I can see I now have a file.txt. This is on my local laptop, not on the supercomputer. And I want to move this file to the supercomputer. So I'm going to use a program called SCP. And I'm going to say I'd like to pick up file.txt. And in terms of the destination, I need to tell it that I want to log in using a username to a remote computer. So I'm going to, in a similar format to SSH, say I'd like to log in using the COU040 username to, and instead of, you might be tempted to type Tectonics here out of habit. I certainly was. But if we did that, that would send it through the login node, which is not what we want to do. We want to send it through the data mover nodes. And the data mover nodes have the datamover.pawsey.org.au hostname. So this is saying, pick up this file, send it using the course username to data mover, the data mover nodes at Pawsey. And we also need to tell it where to put it. It might be tempting to put it in our home directory. So I think you could just put it in tilde. This is saying in the home directory, put it there with the same name, or you could call it something else. But what we should do is actually put it on our Scratch file system. So instead, I'm going to say Scratch courses 01 CAU040. And I'm going to say put it there with the same name, which is what that dot means. So if I press enter, you'll see we've got a similar message from when we logged in. So I'm going to put in that password that's associated with my account. And you can see it's gone and transferred that file across. So now if we then log in, so I'm just going to use Control R and type SSH to find that command in my history because I'm lazy. And here we go again. And I definitely typed that wrong. There we go. Now, note that the MyScratcher variable is on the supercomputer and not on your local system. So I couldn't use it when I had to type it out the full path there. Here, I can just do a cd $MyScratch, which will then take me to that Scratch directory, and I can do an ls. And you can see I have that file.txt there, as well as some other files that I've from later that I put there when I was testing the material. You can even potentially cat the file. And so it's the same file. For that question about the data mover, there is a dash between data and mover, not a dot. So if I just scroll up a little bit, yeah, data-mover.pawsey.org.au. Yeah, it's little things, right? To go the other way, what I'm going to do is also talk a little bit about file management. A good thing to do is to archive your files into sort of compressed versions. So I'm actually going to create a few files here. I'm going to echo text to file2.txt, and I'll echo text again to file 3. So now I've got a few files sitting there, file 2, and file 3. And I'm going to use tar to compress them into one compressed archive. And I'm going to do that using ZCFV. So these options, the Z is saying that I would like it to zip it as well as tarring it. So compress it. The C is telling it I'm compressing something. F is saying that the next thing is the name of the file, and the V is to be verbose. So they're just, yeah, I had to look those up because I just typed them out of habit at this point. So let's call it file.tar. So that's going to be the name of my archive because it's a tarred file that is gzipped. There's lots of different ways that you can name these. Some people prefer .tar.gz. And then I want all the files in this directory, starting with file. And you can see there it's archived file2 and file3.txt. If I do an ls, I now have this file.tar.gz that now contains all of these contents of these files in a nice compressed format. So now I'm going to log out. And so I'm now back on my local laptop and I'm going to transfer them back using SCP. So I'm going to SCP, and this time I want to grab from the remote system. So again, I want to log in. I want to use data mover.pawsey.org.au. And it was sitting there on the Scratch file system in the courses 01 directory, and then my actual username. And then it was the actual file was file.tar.gzip. So I want to grab that file and I want to put it here. So I just use a full stop for that. Again, put in our password. Oops, and I have stuffed up. What did I stuff up? Scratch.
Spelled Scratch wrong.
I did, thank you. There we go. So now, if I do an ls on my local system, I can see I've got a file.tar.gz, and we can do the same thing, except this time put an X instead of a C, so that's going to expand it. Which will probably overwrite the file.txt again and create those other files. So now we've got all our files here on our local system. So that's how you transfer data to and from. Using rsync is very similar. It's just got slightly different commands. Cool.
Do you have to zip it like that to be able to transfer anything?
Nope, you can definitely transfer. So I could have done something like this and just transferred all of the files. It's more, it depends on the scale of what you're doing. And so the question around this question, would compressing large amounts of data stress the login nodes? It depends on how big. So if you're tarring terabytes of files, you may want to actually submit that as a job and do it on the compute nodes. But if it's sort of like up to sort of a gig, it's probably fine. Yeah, if it's sort of hundreds of files, it's probably okay. If it's like tens of thousands, you probably want to do it out on a compute node. And yeah, so, and again, in terms of the transfers, if you've got a handful of files, then definitely, use the star. If you've got tens of thousands of files, you probably want to tar it up because it would just transfer faster. It's in your own interest to do it. Cool. No, these are good questions. Thank you. So I think we've covered all of that, which is good. So there is also the copy petition. So one of the reasons why we were doing that from our laptop is that it's very hard for us to access our laptop from the internet because of those firewalls. So typically you would generally push and pull from your local system from the local system. But if you have other places online, so maybe you're moving it between HPC centers, maybe your institution actually has set up a data storage that is accessible from the internet. You may want to set up automated workflows that sort of run your job and then check your data into those sort of data storage facilities. You can set those up using the copy petition in the scheduler, which I'll talk about a little later. And then you can sort of set up these workflows where you have, okay, I'm going to submit my computational job, and then I'm going to submit a data transfer job and make that dependent on the computational job finishing, which can be quite useful. But we'll talk about that in a little bit more detail when we get there. So that brings us to module 5, making use of the software system. I've been talking for quite a while now. I thought it might be a good time to take a very short break. So I might just pause it for 1 or 2 minutes to allow people to stretch and maybe start again at 11:15.
Yeah, I think that sounds great, Chris.
Yeah, cool. Okay, well, I'll see everyone back at 11:15. Yeah, moving around, stretching is really important. I have known a number of people who have spent a lot of time over their careers doing this, and it won't impact you until sort of 10, 15 years down the track, where suddenly you'll have problems with tendons, elbows, wrists, hips. So yeah, definitely take a break from the computer, stand up, move around. It's really important over the longer term.
Yeah, excellent advice. Yes, everyone get up, go outside, look at the plants. See you back here in a little bit.
Yep, see you in 5. I definitely recommend grabbing a copy of the slides, so you can kind of flip back and through the examples at your own pace. And so you can get those from our Pawsey training resources page, the link at the top there. And then I was just doing moving data in and out. So that was module 4. I can put that link into the chat. Alrighty. So we are talking about using software modules. So the software stack, when we talk about a software stack, it's all of the different pieces of software that are installed. And also often scientific software has a lot of dependencies between the software. So you'll have different numerical libraries, compilers, and different tools that the sort of end user application depends on. And so the software stack sort of is all of those stacked up and made available. And in terms of the kinds of things we have it all modularized into this module system. And within there, you have things like programming environments, so compilers for compiling codes, interpreters for running interpreted languages. We have debuggers for going through and finding the bugs in our code, the profilers for determining what the performance of a code looks like and where it's spending all its time doing computations. There's also these optimized libraries. Definitely you want to make use of optimized libraries to get the best performance. So it's just highly likely that someone that has spent their PhD figuring out the best way to do a matrix operation is going to write a better matrix operation than you. And so using their optimized library is probably a good practice. And we also have the ability to run singularity containers, which I'll talk about later. And we also provide a lot of software that is commonly used. Sadly, we are only a team of so many people, and it's not possible for us to support every piece of install every piece of research software that every user needs to use. There's thousands of users. It's just not feasible. But what we can do is help researchers when they're using the system to learn how to install their own software. We're more than happy to help you learn how to manage installation of your software. And we also, where there's a large number of groups all using the same piece of software, it doesn't make sense for them all to have to install it. So we have a Pawsey provided software stack containing those commonly used programs that have been compiled up to be really performant on the system. So that software stack that we provide is located under /software/Photonics. And the software that you install should be in your /software directory and /software/projects, your project ID, and if you're just installing it for yourself, your username. So what should you be using to install your own software? At Pawsey, we've started using a tool called SPAC, which is a very powerful tool that supports a lot of scientific software that will automatically build and install the software for you if needed. There's also containers, which I'll talk about a little later. If you're using Python, we recommend using pip to install the packages, although there's also things like Conda as well. And otherwise, if it's not supported by any of those, sometimes you need to manually install the software. We're not going to go into too much detail on the specifics of installing software in this training this morning because it would take too long. But if you are stuck installing something, feel free to open up a help desk ticket and we can help you with specific issues that you're running into. So I've mentioned modules. What are they? Modules are a way of having lots of software installed on the system, but not necessarily loaded. And the reason for this is that sometimes you would like to have access to multiple different versions of the same piece of software, or it might be that two pieces of scientific software in different domains have the same name, and you want to be able to differentiate between them. And so you really only want to have things in your environment that you're actually going to use. And the module system allows us to install all the software on the system and then use modules to load the pieces of software that we want to use. The particular module system that we're using is called LMOD, and the command that we use to make use of it is the module command. So let's go have a look at what that looks like. So I'm currently logged out. So the first thing I need to do is jump back in. And I have a bad habit of typing my own password when I do that. So I just press Control-C there to cancel, and just so I can start again, because I don't want to set off that blacklist. Excellent. So the first command I'm going to go with here is the module list. And this lists all the modules that are actually loaded by default when you log into the system. And we'll go into some of these in a little while, but you can see there's lots of these modules. Some of them have versions associated with them. So there's a module name, then a module version, and there's a couple of them that are not versioned. So another command that's really useful is module avail. And this is going to print out all the available modules on the system. So you can see that there's quite a lot of them. If I press enter, it will go through them. And you can see that in these sections, they're sort of grouped. And this is telling us the location of the software, or at least the modules for the software. And so it's grouped into different categories. There's our MPI, some astronomy applications, bio applications, general applications, libraries, programming language, utilities, things for benchmarking, and other tools as well. So that's useful for seeing what's there. And in terms of loading a piece of software, we make use of the module load command. So I can do a module load and say I want to use NWChem. I'm going to naively type NWChem in there, and it's going to complain at me because I haven't specified a version. And so one of the things that is new to Photonics, if you've ever used Magnus before, is that for the Pawsey provided software, we've insisted that you provide the version of the software that you're planning to use, and we've found that this has made it easier to have less unexpected behavior cropping up. So I've now loaded the NWChem module, and it doesn't really seem like much has changed. But if I have a look at which NWChem, and hopefully that is the name of the software, it is, that's great. So you can see here, if I was to type NWChem, so to run the NWChem program, this is the program that would be running. So you can see it's sitting in software, Photonics, because it's in the software stack. We've organized our software stacks by date. We have the architecture that it's run on, the compiler it was compiled with, and then the name of the actual piece of software with a hash that is something that SPAC produces when it builds things. We're in the bin directory, and this is where it's found. And so the reason it can find that is because if I echo an environment variable called path, this is a column separated list of all the directories that the shell will search for a file called NWChem. And you can see that this directory that it's sitting in is at the front here. So the first place it looks, it's going to see, oh, there's NWChem. This is the particular program that I should run. And so really what that module load has done is it's inserted that at the front of that path. And so if I do a module unload, NWChem, it will unload the module. And if I echo that path again, you'll notice now that this is no longer there. It's starting straight with the next one. So it's removed it from the path. And so if I do a which NWChem, it can't find it. It's effectively hidden from the environment. So let's come back to the slides. think we've covered off that. So in terms of some notable modules, particularly ones that are loaded by default, you'll notice there's a progenv GNU and a GCC. So this is the GCC compiler that a lot of the software on the system is installed with currently. There are a couple of alternatives to this. There's also the Cray compiler, which is loaded by that progenv Cray, and the AOCC compiler, which is loaded by progenv-AOCC. And there's also our MPI library, which is what is used for doing that parallel communication between lots of processes that are run on the system. So a lot of supercomputing codes will make use of MPI, and so that Cray MPICH provides the MPI library that allows that communication. And the architecture-specific optimizations are enabled by this Cray PE-x86-Milan module. And so that's important to have the right module for a architecture loaded. Currently, most of Sotonix is that Milan architecture. So it's relatively straightforward. You don't really need to worry about it. But typically, as supercomputers get a little older and get other things added to them, you might end up with more than one CPU architecture in different partitions, and it might be that you want to switch between them depending on which partition you're using. So module avail, as we just typed it, if you don't include anything, we'll show you everything that's available. You can narrow it down by typing that substring. So if we typed, and feel free to follow along, a module avail NWChem, it would just provide all the matches to NWChem, which is quite helpful. So I think I've already done this demo. We'll keep moving. So one of the things that we have done in our software stack is that we've actually baked all the dependencies into our software builds. So generally when you're running a piece of software, it will know where its dependencies are, which is helpful. I think I've done this. So here's an exercise. Have a go. Have a look at the GROMACS package and see what versions are there, and just follow through, have a look at CMake, and just see how you go. And I might be quiet for a minute or two to let you have a go, and then I'll follow along shortly. Yeah, that was a good question, how to exit from the printout of the module list. And yeah, Q is the way.
Chris,
Yes.
how do you check for other versions, like for GROMACS?
Yeah, so that's a good question. So if I'm doing a module avail GROMACS, you can see there's two versions there. There's
Yep.
a 2020.4 and a 2021.4.
Yeah.
Does that make sense?
Yeah, that's good. Yeah. So,
Cool.
Thank you.
Bash Q command not found. I feel like at that point you've already quit and you're back at the command line, because it looks like if I've already quit out of it and then I just type Q, I get that. So if I was doing a module, is it module avail that was, yeah, so here, like I can go up and down with my arrow keys, and then to get out of it, I just press Q and then I'm back at the command line again. Also, you've done that and you can't type anything here. Yeah, it might be worth closing it off and logging in again if you get really stuck. Yeah, exactly. Alrighty, so I guess just to continue through, we can do a CMake -- version. And you can see we've got version 3.17. And if I do a which CMake, so CMake is a piece of software that is used for building compiled C programs. And you can see it's in /user/bin. So this version of CMake is not provided by the module system. This is provided by the actual base operating system. And if we have a look at that path environment variable that we're searching through, you'll see here user bin is right about there. So when I'm typing CMake -- version, the shell is going through that whole list until it gets to user bin and goes, oh, there's a CMake, I'll run that one and see what happens and provide the output. So if we do a module avail CMake, we can see we've got a newer version available through the module system. And so sometimes you'll find if you're using CMake to build software, it'll say, oh, you need a newer version of CMake than you currently have installed. And so you do a module load CMake 3.21.4. Because it comes with the operating system, it's just there. And so anything that's just installed with the operating system. So this is the based on the SLES Linux operating system. And those packaged operating systems tend to have slightly older versions of things. And so if you're installing something yourself, it tends to be slightly newer. And we don't know if all of our researchers need CMake. So what we don't want is to have, when you do a module list, a whole heap of, like you don't want hundreds of packages here that are all loaded to give you the latest versions of everything. We'd prefer to keep it as lean as possible. So if you do need a newer version of something, you can just load that newer version. And if you can just use the default, then it's probably easier just to use the default. For most of the things that we're talking about, they're not things that if the performance particularly matters. They're not the scientific codes. They're more just utilities that you're not really going to notice much of a performance difference between an older version and a newer version. It's just if it happens to have a feature that you particularly need. Good questions. Where were we? So I was talking about CMake. And so we've done that module load CMake. And so now if I do that CMake -- version, you can see we've got the version provided by the module. So not all software builds with all compilers. which is quite unfortunate. Sometimes when we're coding, particularly if we're developing software and we're only compiling it up with one compiler, we might not realize that we're writing code that only works with that compiler. And so it's actually a good practice if you are writing compiled code to compile your code with different compilers and be aware of where your compiler is letting you get away with things that probably isn't conforming to standards. And so that's why we have these different progenv modules, and we use the module swap command to switch between those programming environments to get access to the different compilers. And so different compilers might be better for different codes. In particular, the Cray compilers are very good for Fortran codes. So let's have a look at module swap. So what I'm going to do is I'm going to do a module swap. I'm going to swap from the current programming environment, which is the GCC one. So you can see that in my last module list here. I'm glad to check that. And I'm going to swap across to the progenv Cray. So I'm swapping to the programming Cray environment. And you can see that it's reloaded a couple of modules. And if we do a if we just go with CMake, you can see we've got this path to CMake here. And if I swap back from Cray to GNU, you can see it's automatically reloading these modules. And then if I do that command again, which CMake, you can see it's actually it's finding a different CMake. This CMake is in this directory, whereas this CMake is in this directory. So it's actually, we have a different installation of the software that has been compiled with the different compiler. So by switching between these programming environments, you get access to the software that's been compiled against those particular compilers. And you may find that some pieces of software have only been compiled with a particular compiler because they don't compile with the others. So I think there's an example here with MWChem where it tells you there's inactive modules because there isn't a version of MWChem with that other compiler. So that's something to be aware of. So that's the main module commands that you'll need. There's a couple of others that we haven't covered off on. What is will tell you a little bit about the module. Help will provide more information as well. I like to use module show, I think, which will show you the paths, which can be quite helpful. I might just do that very quickly. So I do a module show NWChem, for example. It provides you with some information. It will tell you what other modules it's dependent on, and it will also tell you what it's doing with all the paths. So you can see here it's prepending the path that we saw when we were looking at that path variable with the location of the software, but it's also putting setting some other environment variables as well. So if you're unsure of what a module is doing, using a module show it is quite helpful in finding out what's going on with all these paths and environment variables. On Topaz and Garawala, because it's not a HPE Cray system, there isn't the progenvs, you just have the straight compilers. So you'll switch between the GCC compiler with other compilers that might be available on those systems, which you can find through doing the module eval. You also might have different modules for the architectures. So in this particular example, there's a Cascade Lake architecture. So you may find things are a little bit different. So it's worth doing that module list and module avail and having a look around when you get on those systems. We do have some policies. As I mentioned, we do what we can to provide software that lots of people use, but we don't have enough effort available to install everyone's software for them, unfortunately, but we are happy to help you learn how to do it. We don't pay for any domain software licenses. We do have licensed compilers and debuggers and profilers, but if for your actual scientific code, it's up to the research groups to provide those licenses. We do have a couple of pieces of software that are commonly used where they are licensed software, and you, depending on the terms of the particular licenses, for some of them you can just provide your email and we'll go check it against a licensing portal for VASP and then add you to the VASP group so you can use that piece of software. For others, you have to kind of set up those firewalls, or it might have already been done for you to make use of the license server sitting in institutions. So for, say, ANSYS products and Fluent, they will run and check out licenses from institution. We do have some documentation on building software that is worth checking out. That might be helpful, and yeah, we do our best to help everyone we can, but we do have limited effort to support the broader range of scientific software installation. Are there more questions on the module system? Feel free to continue typing. Oh, here we go. No, there is no module system on Nimbus. You are very much on your own. So for that, you will probably mostly rely on the package manager of the Linux distribution that you choose. Different flavors of Linux have different package managers that will install package software for you. Because you are the administrator on a Nimbus instance, and you can also use some of the tools that we have on talked about earlier, such as you know, if you can just use, you would install Python using the package manager, and then you could install pip using the package manager, and then you could use pip to install lots of Python packages, for example. Yes. Yeah, so the question is, are you essentially building your own system? Yeah, so the cloud is very much, you have complete customization over exactly what you want. And that can be quite useful, as we'll see when we're talking about software containers. So one of the drawbacks of using the supercomputer is it is based on a particular Linux distribution, and some of the scientific software has been written such that it only builds against a different Linux distribution, which can be quite frustrating. And so containers are one of the ways that you can get around this issue. And what it is it's a sandbox that isolates the application and all its dependencies. And it relies on a container runtime system that will sort of pick up the container and run it for you. So the advantages of this is that you have a lot more reproducibility and portability. You can kind of pick up these containers and run them on different systems and have them doing the same thing. You can sort of build the container once and then download it and run it in lots of different places. And you can also make use of the MPI parallelism on the supercomputer, but it starts to get a little bit more complicated because we have to start poking holes in the container. So it's what's called pass-through. So we expose the MPI implementation within the container. And there's some benefits to doing that, which I think I'll talk about shortly. But there are also drawbacks. So one is that by compiling on a different architecture, you're not necessarily making use of all of the features of the particular architecture that is on the supercomputer. So there may be a slight hit to your performance, which is not desirable, because one of the main reasons you're coming to a supercomputer is to make the best of your performance. You're also limited in terms of being able to manage the container runtime. You're kind of stuck with the runtime that we provide, because it requires root access to install the container runtime. And there's a lot of effort that goes into providing MPI support, and I believe you kind of have to use customized containers to make use of that MPI support. So you have to kind of build your own container specific to that MPI installation. Some good use cases: if you have a ridiculous amount of software to be installed, so we see this often in the bioinformatics field, where you've just got hundreds of packages, and rather than going through and installing them all, you just grab a container that contains them all and run it. If you have really complicated builds with lots of dependencies, so again, deep learning is a good example of this. That can also save the time of going through and getting it all sorted out manually. If you have lots of dependency trees with package conflicts, so Python and R workflows, it can be helpful. And so most of those use cases that I've talked to so far is about managing the fact that you've just got lots of software to get through and install, and it's easier just to pick up something where it's already done for you and run it. The other interesting use case for containers is that the container appears to be a single file to the file system, and performant file systems really do not like where you've got large numbers of small files. And so OpenFOAM is an example of a piece of software that potentially can do this, where it just wants to access lots and lots, like tens of thousands of little files, hundreds of thousands of little files, and it really makes the file system start to struggle. And so by putting all that in a container, the file system just sees that one container file, and that's really helpful for simplifying that I/O, the input/output, the reading and writing of files to the file system. So the runtime that we use at Pawsey is called Singularity. So you can do a module load Singularity. I suspect the version may have changed since these slides were written. So you may want to do a module avail Singularity first and just check that version number. There are some configurations from the Pawsey staff to reduce the learning curve. So if you're using some of our Pawsey created containers, we make relevant file systems available in the containers, so you can see Scratch and software and other file systems, as well as make that MPI implementation available as well, which can be quite helpful. And I'll talk a little bit about container modules shortly. So definitely there are a selection of Pawsey curated containers for some of these use cases where it is helpful. What does running a container look like? Let's have a quick demo. So if you're familiar with containers, you can go to hub.docker.com to Docker Hub, and there's lots of containers there that you may want to make use of. And what I'm going to do is sit into my Scratch. I'm going to remove my example that I did earlier, and the first thing I'm going to do is to find that Singularity module. So I'm going to do a module avail Singularity. You can see there's a few there, and we're going to grab 3.8.6. So I'm going to do a module 3.8.6. Oops, no, I need a Singularity in there as well. List. So that's now showing up in our loaded modules. And the next thing I'm going to do is I'm going to pull a container image from the Docker Hub. So this one I've looked up ahead of time. So I'm going to use the singularity command. I'm going to tell it to go pull a container image, and we're going to use Docker, and we're going to pull the Ubuntu image, and we're going to grab 22.04 just as an example. And Singularity has grabbed that recently, so it's sitting there cached. I think when I ran this yesterday, it took a little bit longer. And you can see now I have this .cif file sitting there. So now what I'm going to do is I'm going to run this container image and run a command in it. So I'm going to use Singularity to do that. We're going to tell it we want to execute a container. We want to execute this container. And the command we want to run inside the container is we're going to cat a file in the etc file system called os-release. And this is the version of the operating system. You can see it's taken that, it's just run the container, and that file, according to the container, is Ubuntu 22.04, which is very interesting because if we cat the actual etc OS release without running the container, you can see that the operating system that we're actually running on is SUSE Linux Enterprise 15. So this is really powerful. We've just run a completely different operating system in a container on the supercomputer, and this is really helpful if you have a particular piece of software that is the installation is only provided for that particular Linux distribution, then this is a really handy way to be able to run it on the system. And so there's some links to some online registries here in the slides if you want to grab them off the website and follow them and have a look, and that can be really useful. There's generally tags that are associated with containers, and it's generally good to use a particular version tag. You notice I use the 22.04 tag. There's also tags like latest. We don't recommend using those because what that points to will change over time, and that takes away from your reproducibility. So we saw those key commands. If you need to run GPU-enabled containers, there's some -- NV on NVIDIA GPUs and -- ROCm on AMD GPUs. So if you're planning to run machine learning containers on Topaz, you're going to want to pay attention to this one. And whoops, if you are planning to use phase 2 when it's finally configured and available, then you want to use the -- ROCm. I think we've done that. Feel free to have a go. I feel like we're running a little bit behind time, so I might leave this for you to have a look in your own time. But you can definitely try running different versions of Python from what's available on the system using containers from Singularity, from pulled down from Docker. So another interesting thing that can be done with containers is you can actually provide them as a module in a way that you don't really realize you're using containers. And so there's something called the Singularity Registry HPC, or SHPC. And what this does is it kind of wraps up the Singularity execution with with also entry points for the software commands that you want to run in it. And we've actually, for some of our modules on the system, we've used this. So for a lot of the bioinformatics packages and OpenFOAM, we've used HPC, and we've basically installed the container as a module using SHPC. And that means when you're actually once you've loaded the module, you don't need to use Singularity commands to use the container. You're just using, for in this example, we've used HPC to install Python as a Python container as a module. And then when you module load it, you just run Python, and it's actually hitting the entry points to that container and running Python inside the container, which is really cool because it just simplifies everything a little bit. So I think that brings us to the end of talking about installing software. And so from here, we delve into actually how to run things on the supercomputer. And this is probably a good point to take a slightly longer break. So I'm not sure, Emily or Edric, how long that should be.
I mean, about 30 minutes to grab some lunch seems.
Yeah, no, it sounds pretty good. I was thinking the same thing. So let's have a half an hour break. We'll come back at 12:30. I will probably be around on and off during the break. So if you do have questions, definitely keep throwing them into chat, and I'll get to them when I can. But I'll see you all in half an hour. Do you have a command for loading R? Yes, I think it's available as a module. So if I do a module avail R, you can see it's just here. So you could do a module avail, sorry, module load R 4.1.0, and then that loads it for you. And I assume, I'm not an R user, but module show R, that has put this directory into the path. So if I have a look in that directory, oh, it's capital R. There you go. So the reason we use Singularity is because it's a shared operating environment where you don't have root access. The entire purpose of Singularity is to provide Docker in that environment. So on your cloud instance, you can just use Docker to do all of your container stuff because you have root access. Yeah, it's if you're on the cloud, it's your computer to administer, or your instance to administer how you see fit. So anything you can do on your local laptop, you can do on that. You've got full root privileges. Yeah, and yeah, I'd imagine you would use Docker for using running containers on your own image. Yes, so it's worth noting that for Singularity here, we were pulling from the Docker hub. So we were pulling Docker containers, but using Singularity to run them. Cool. Well, I'm going to take a quick break, but feel free to keep posting questions, and I'll come back and answer them in a little while. So what is an accounting model? The accounting model is a method to define and measure the usage when we're running computational workflows, and the unit of usage is a service unit, and that measures how much of the supercomputer we're using. And so the definition of a service unit may change from one supercomputing center to another, but typically an SU usually relates to the hourly usage of one of the CPU cores on the supercomputer. So at Pawsey, one service unit is what you spend if you're using one physical CPU core, one of those light blue boxes on the diagrams from earlier in the training. If you're using one of those for an hour, that's one SU. So given there's 128 cores per node, if you're using a whole node for an hour, you'd be charged 128 SU. And so to calculate the cost of any particular arbitrary job or program that you're running on the supercomputer, you're multiplying the number of cores that you're requesting by the wall time in hours. So how long you're making use of those compute nodes for, or those cores for. And so in order to figure out what we can do with the supercomputer, what we do is we take all the cores on the system and multiply it by the hours in the year, and that's how many core hours or service units we have to give out. So here's just some examples. One service unit is an hour of using one CPU core or half an hour of using two CPU cores. And if you're using one of the nodes on our old Magnus system for 24 hours, it would have cost you 576 SU because it had fewer cores, whereas on Photonics, because it's got more cores, you only get 4.5 hours. So hopefully those cores are providing you with additional performance to make best use of that. So in terms of the consumable resources that we have on a compute node, we have those 128 CPU cores, and we also have the random access memory, or RAM, the memory of the node, that varies depending on the type of node. And we allow shared usage on the supercomputer. So that means that if you want, you can use up 2/3 of a node and let someone else use the other third and not get charged for that usage of that third. So this is a way of, I guess, efficiently using your allocation if you don't need a full node to run your job. And so the issue there is that if we have someone running on one core but needing all the RAM, then people can't make use of those other cores. And our solution to this is to charge the largest fraction of either. I think someone might have their mic open. If you could mute it, that would be great. So in this example on the right, we have 6 cores, of which 3 are being used. But then in terms of the amount of RAM available on the node, 2/3 of the RAM is being used. And so in that case, we would charge for 2/3 of the cores because that core that isn't being used is still in some ways prevented from being utilized because the RAM associated with it is used up. It's also worth noting that if your job finishes early, so if you say asked for a job to run for 8 hours and turns out it only needed to use 2 hours and stopped, then you get charged for your actual usage, not what you request. So these are some more examples. In example 1 on the left here, we see we're using half the cores, 2/3 of the RAM, and so you're charged for 2/3 of the node. And this example, we're using 2/3 of the cores, but 1/3 of the RAM, and again, you're charged for 2/3 of the node. So it's just the larger proportion of whichever one. So some more examples of estimations. So say you wanted to run for 24 hours on 8 nodes. So you take your 24 hours, multiply it by your 8 nodes, and then multiply it by your 128 cores per node. And you'd end up with that job would consume 24,576 service units. Say you're running for 10 hours on just 32 cores within a node, you just multiply that out and get 320 service units. And another thing you can request is exclusive access to a node. So here in this job, if you wanted exclusive access to the node, so the whole node's yours, but you're only using some of the cores, you're still getting charged for all the cores on the node because other people can't make use of them. And here's an example that looks at the maximum fractional amount, which I think we've covered off in detail already. So in terms of allocations, what we have currently is a yearly merit allocation call that happens in the second part of the year. And this is for the large allocations on the system. And research groups write merit allocation proposals to request time on the system and provide details of how they're going to use the system, both, I guess, scientifically as well as computationally, and to provide a justification for why they need that time. And then an external panel of scientific experts and scientists will will review the applications and get together and meet and decide how much time each of those applications should receive. And so your project will have an allocation associated with it. We used to have just the allocation available for the year, and we had an issue where a lot of projects would not use their allocation until towards the end of the year. And sadly, we can't support all the projects using all of their allocation in December. We need everyone to sort of use their allocations throughout the year. So for that reason, we divide the yearly allocations evenly into quarters. So you need to use your allocation through the merit process within a quarter, or else you kind of lose it. And the accounting is set up around the principle that all projects should get a fair share of usage relative to the awarded allocation. So if you're halfway through your allocation, you should be sort of have a similar priority to someone who is also halfway through their allocation, regardless of how big their allocation is. And similarly to storage, we really encourage everyone to monitor the allocation usage. The last thing you want to do is accidentally spend all your allocation and then not have enough left to do the work that you need to do. So keeping an eye on it is quite important. So how do we actually do that? Let's have a look at a demo. So if I can find my terminal, we are happily still logged in by the look of it. Yeah, that's great. So what we want to run is Pawsey account balance. We ran this earlier with the -S for the storage. We can just run that as is. And you can see here for the courses 01, the group that we're in, we've practically used nothing because we haven't really submitted any jobs yet. To provide you with some perspective of what this might look like for a different group, I can do this with a -P for project, Pawsey 0012, which is the one that our team uses. And I can do a -U to show users as well. And so you can see here of this 5,075 SU allocation, we've used sort of 5% of it this quarter. You can see some of my colleagues and the usage here. So this can be quite helpful if you're trying to keep an eye on how different members of a project are making use of the allocation. And so I think I've just covered all that. So that's allocations. Were there any questions on that so far? I'll take that as a no, but feel free to keep typing if you are. So we now move on to actually scheduling jobs. So I've mentioned the term job a few times. So this is the unit of computational work that's executed on the supercomputer. When you're submitting a job to the supercomputer, you're saying, here is some work that I would like you to run out on the compute nodes for me. and you're providing information on what that might look like. And then you're providing that job, information about that job to the scheduler, which will then identify when some compute nodes will be free to run that for you. And then when they are free, it will then run the job on your behalf. So that's a really important thing to really understand, is that typically you won't be using the system interactively. You're wanting to create job scripts or Slurm batch scripts that contain all the instructions that you would like the scheduler to run on your behalf when it runs it. And this is really helpful. For example, if you think about those compute nodes that have 128 cores, if you're just sitting there for a minute, not doing anything when you're interactively logged into an entire node, you're sort of burning through sort of hundreds of service units every hour that you're not actually sort of typing anything. So it's important to have it all automated and put into these scripts. So we're logging into the login node to submit the jobs, and then the scheduler is going to execute the jobs on the compute node. And as I've mentioned, you shouldn't run computationally intensive things on the login node. So a good way to think about a job scheduler is a bit like a calendar planner. So if you've ever used one of these to schedule when you're going to be doing things, it kind of looks a bit like that. And what we see here is one of our, I think it's now 3 generations back, an old shared memory machine that we had that had 192 cores, I think. And the reason we keep this image is because it's sufficiently small that you can still make out individual jobs. As you get bigger systems, it becomes difficult to actually come up with a graphic that's easy to see what's going on. And you can see on the vertical axis all of the cores on the system. And then in the horizontal axis, we have 24 hours. And all of these rectangles are jobs that the users were submitting, and then the scheduler was running on the system during that 24 hours. And so you can see these yellow rectangles here. There's sort of 4 of them the same size. That's actually one job that's sort of spread over these ranges of cores that sort of ran from midnight through to sort of midday on that portion of the system. And you can also, I guess, get an appreciation for how densely packed this is. There's no or very few empty spots. Most of the cores are taken up by jobs that are actively running. And so effectively the scheduler is just playing Tetris with all of the different job sizes that the researchers are requesting on the system. So one of the really important things to change about your workflow is you don't want to be waiting on your results. If you submit your job to the scheduler, once you've got a significant computational job, if you submit it to the scheduler, whatever you do, don't sit there waiting for it to complete. You will go slowly mad. You want to submit it and then go do something else and come back later when it's likely to be done. And ideally, if you've got a lot of computational work to do, what you want to be doing is you want to work on preparing a job, submit that one, then start working on your next job and submit that one, start working on your next job and submit that one, and get as many jobs into the queue as possible, and try and automate as much as you can as well. So we assign priorities to the jobs, and we have what's called quality of service levels. And this is to ensure that jobs should be run fairly on the system, and to try and give you some control over how quickly your jobs get run. And so usually when you submit a job, it'll have a normal quality of service. And if you use up all of your quarterly allocation, we allow projects to continue running jobs. And our reason for this is there's usually some projects that don't use all of their allocation, and we'd prefer that time not to be wasted, because it's an expensive computer. If the projects that were allocated the time aren't going to use it, would rather other projects that have finished using their allocation can make use of it. So, but what we don't want is those projects that have used all their allocation running when there are jobs that haven't, that still want to run. So we're using these quality of service levels. So once you've exhausted your allocation, you then go into this low quality of service. So if there's any jobs that are at the normal quality of service, they will get priority over you. But if no one's using the system because everyone who wants to use it and has allocation left can't make use of it, then potentially your jobs can still run up to 150% of your allocation. Once you hit 150%, we then cut you off. So other projects can fairly have an opportunity to make use of that over allocation, and the levels reset at the beginning of the quarter. So this is why it's important to keep an eye on how much of your usage you're using. You don't want to end up in a case where you can't run jobs for a period of time. We also from time to time have requests where researchers get in touch and say, I've got an urgent paper deadline or a proposal that I need to have complete, and it's really urgent that this work gets done. And so we actually provide up to 10% of your allocation. You can manually specify a high QoS, a high quality of service. And so that way you can kind of self-serve and self-select what you think is urgent. But once it's gone, it's gone. So that can be helpful for those situations as well. And finally, we also have a highest priority. And so this is reserved for, I guess, extremely significant work. Things that come to mind was we had a lot of special projects with the pandemic, researching the COVID-19 virus. We've also had workflows run when airplanes have gone missing to try and figure out where we're likely to see debris to kind of get an idea of what happened. And so there's sort of, significant occasions that come along, and those jobs typically sort of run at the highest priority. So we have a little bit of terminology. We have the scheduler on the system is called Slurm, and it has a concept called clusters. And so a cluster is all the compute resources managed by the same instance of Slurm. And these basically map to our supercomputers. So there's a Slurm cluster for Photonics, a Slurm cluster for Topaz, and a Slurm cluster for Carawalla. And so the Photonics cluster is then divided into petitions. And the petitions are the different types of queues of jobs. So there'll be particular features of the nodes in a petition that make it sensible for us to separate them. So the petitions on Photonics, we have the work petition, which contains the regular compute nodes. And this is the default if you don't specify a petition. We then have a debug petition. And so this has a shorter maximum wall time that you can run jobs for. So typically jobs on the system run for a maximum of 24 hours. And we do that to make sure that we're not risking a job crashing and losing a lot of information. So by forcing jobs to finish every 24 hours, it means that longer jobs typically get chained together as multiple 24-hour jobs, and there's sort of checkpoints in between them so that we don't lose millions of core hours of work because one of the nodes went down after something's been running for a week at scale. But the debug petition is a lot shorter, and the idea is you should only be running it there if you've just got something quick to do. So we would like those nodes to be mostly idle and free. So the work petition we want to have running all the time. The debug petition it's just a few nodes that are free and available. So if you need to quickly test something, you can jump in there and test it without having to wait to get on the system. So please don't run production work in a debug petition. It's just there for sort of testing and developing things. We also have a high memory petition, which has that larger amount of memory. So it has up to almost a terabyte of memory per node. So that can be helpful if you have jobs that require a lot of memory. And we also have a long petition, which will let you run up to 4 days, but it's limited in size. So the risk of losing a lot of compute time is mitigated because there's only a few nodes in it. Finally, I've talked about the data mover nodes earlier. So we have the copy petition, which will let you actually run jobs on those nodes and control it from the scheduler. So this can be really helpful if you want to automate, say, storing your data into Acacia after you've finished running your compute. You can have a first job that runs in the work petition and then another job that runs in the copy petition that is dependent on that first job completing successfully. Finally, there's also the ASCAP T petition, and this is reserved for the operational work by the ASCAP radio telescope scientists. So let's have a little look at these petitions in more detail on the system. And the command that we're going to be typing is sinfo. And you can see there's a lot of information here. There's the titles of all the columns here. The names of the petitions are here in this first column, although you'll see the node list is sort of spilling over into some of the lines here, which can make it a little bit more difficult to read. But you can see there's multiple entries for the work petition. And the reason for that is that there's a line for each state of the nodes. And so you can see the node count that are in that state here. So you can see there's 15 nodes in the reserve state, 16 nodes that are in planning state, 9 nodes that are down, 128 that are mixed, and 141 that are allocated. And so this is a way of getting a sense of how busy the system is. So one thing you'll notice is that there are no nodes in the work queue that are idle. If we come down and have a look at the debug queue, however, we'll see there's 7 idle nodes. So that means it's going to be relatively easy to grab a node quickly in the debug queue, whereas for the work petition, we're going to be, if you want exclusive access to a node, there's no idle nodes at the moment and you're going to have to wait in the queue. There's also some more information here around the time limit on the jobs. So you can see most of them is 1 day, this 1 day. Copy jobs can run for 2 days. The long petition can run up to 4 days. And we also have some information on how many cores are available. And so if you remember, I was talking about sockets and cores earlier today. You can see that most of these nodes have 2 sockets, with the exception of the copy petition, which only has 1 socket or 1 processor on those nodes. We can see that each of those sockets, for the most part, has 64 cores for a total of 128 cores in total, apart from the copy petition, which only has 32 cores. And then we have support for multiple threads per core, which is something called hyperthreading, which may be of interest if you're running threaded codes. So let's come back to the slides. So that's so finfo was showing us what was happening in the petitions. And so that was more looking at the availability of the actual nodes themselves. We now can look at the queue for those nodes and for those petitions by using the sq command. So if I just type sq, we get a very long list. So you can see there's lots and lots of jobs here. In particular, D35 has a large number of jobs at the bottom. If I scroll up a little while, we can see some other groups. There's ASCAP Ops jobs there waiting. And if we come up to the very top, we can see jobs that are actually in the running state. So this state R, they're running. You can see the node that they're running on. This is the primary node that they're running on, and not the full list that we were seeing before. You can see the job ID, which is the identifier for the job, a numerical identifier. You can see the user, the account, and when it started and when it's expected to finish. Now the job might finish sooner than this. This is just how much time has been requested for that job. We also see the priority. So typically the scheduler will run the job with the highest priorities next. So if we come down this list following these R's, eventually we'll get to PD for pending. So these are jobs that are not running, they're queued, and you can see roughly when they're expected to start running. But that may vary depending, like if someone with higher priority comes and submits jobs, these times may change. And you also see a reason for why they're not running yet. So these jobs are not running because of priority. There's other jobs that are sitting here waiting on dependencies to finish. And there might be other things as well. Probably a good point to come back to the slides, if I can find them. Oh, what have I done? Oh, there we go. One key. Cool. So that's a lot. So one thing you can do is use commands like head, less, word count, top to kind of chunk it up. But usually what's more useful is to narrow down your search of which jobs you're looking at running. So often you'll be interested in what jobs are running within a petition. And so -P and then the petition name can be helpful. You might want to only look at the jobs that you are running, so --me. You might have multiple projects, and so you might want to specify a particular project account with --account or -A, and the project name. Or maybe you want to see what colleagues are doing in your project, so you might want to specify their username. And it's actually very customizable what columns it shows. And so if you look at the help pages for SQ, you can see you can actually specify a -- format and then just provide a list of different columns that you'd like to see, and they can customize it. So definitely, I think there's an exercise here. Have a go working through this one. Try and count the lines to see how many jobs are queued. Maybe, yeah, try and restrict your search to just the petition queue and see how many jobs are queued there. And just have a little look around and have a go at trying out those options. And I'll give us a minute or two to have a look at that. And yes, the time taken is just the actual time that your job took to finish. This is what you're accounted for.
Chris,
Yes.
say someone was had like a job queued, and they wanted their name or like user ID to be hidden for whatever reason, such as I don't know, like deadlines or two people are working towards the same project, like who gets their first count. I don't know if that's relevant, but if they wanted to hide their username, is that a...
Yeah, so you currently can't hide the username. We did look into, there is the ability to hide some of the output from other projects in the scheduler output for SQ. However, you can still see it in a lot of the other commands. So we did look into it, and unfortunately Slurm doesn't have the functionality to fully hide that, and so we figured it was easier just to leave it as is. So what can be seen is the username of the person running the job, and I think the location of your job script, if you sort of dig down into the job information. That said, you can't see the actual contents of the script or what that might be. I did used to work for one of the team leads when I first started. Got in trouble because he called his supercomputing jobs tombRaider.exe. And yeah, had people contact him and saying, what are you running on our supercomputer? So you can change the name of the job, but I think the username and the project is visible.
Yeah.
Alrighty, so let's have a quick look at this. So if I do an SQ with just the copy petition, so -p copy, we can see nothing's running in the copy petition at the moment. The work petition, I think, is probably where most of it is. And I think was there someone using the debug node, or was it down? Oh, no one's using the debug node at the moment. So relatively easy to copy data and debug at the moment, but you're going to have to wait in the queue to run. So to do that word count, if we just do the work queue, the work petition, we can pipe it into word count, but if we use the -h flag, it will remove the header. So that first line with the headings, and so that way we'll get an actual count of the jobs. And so I'm piping the output of SQ into the word count command and using the -l to say how many, to get it to tell me how many lines there are. So there's currently 1,169 jobs in the queue, and for the work petition. The next thing we're going to look at is actually trying to have a glimpse at a job that we are running. And so we're going to jump forward a little bit and look at actually submitting jobs. So what you want to do is cd into your MyScratch directory and run this git clone command. And that will download our training exercises. And if you then go into this directory, into the job scheduling overview inside that, you can then just do an sbatch first job.sh and then try an sq-me. And then you will hope that job basically sort of prints out the time every 15 seconds for a minute or two. So you should have an opportunity to see your job running. So that's a lot. So I'll walk us through it, but feel free, particularly if you've got your own copy of the slides, to go ahead if you're keen. So I'm already in MyScratch, so I've already done a cd $MyScratch, and I've actually downloaded already. So I'm going to remove that, so I can just show you how to do that again. So what we want to do is type a git clone, and then that address, which was on github.com, and Pawsey-SC, and it was Supercomputing user training. And I'm going to deliberately put a typo here by deleting the G. If it's asking you for a username, you have not typed it correctly. So you can just Control-C out of that. And then hopefully I have now typed it correctly. Time will tell. I did. So you should see this, which is it going out to GitHub and cloning our repository there. And so now when I do an ls, you should hopefully see there's a Supercomputing user training directory sitting there waiting for you. And if you cd into that directory, do another ls, you can see there is a what's it, job scheduling overview. It's from memory, but I'm hoping that was the one. And do another ls. Yeah, and we can see a first job.sh. So if we just do an sbatch, so this is submitting this job to the scheduler saying, could you please run this job for me? What you'll find is potentially it might just run if it can find a space. We've actually set up a reservation for the training this week. So I can just show you briefly. Show reservation. So these are all the reservations on the system, and you can see here we have this reservation, which I've not yet tested, but I'm hoping it's all configured and going to work okay. But so we should be able to do an sbatch -- reservation equals interns. And then that first first job, and hopefully that will use our reservation to run the job, so we don't have to wait in queue. It's possible that there's enough mixed nodes that there's free cores available for us to jump into anyway, but this will guarantee that it runs quickly. And so then if you do an SQ --me, we can actually see our job running on the system, which is pretty cool. So eventually that will stop running, but we can come back to that when we actually look at. So I've done a lot of stuff here that I have not covered yet. The intention there was to let you see a job running in SQ-me, and so we'll go into this in more detail shortly. I suspect, so there's a question, does a job have to build in its time constraints? Yes, we strongly recommend doing that. There may be a default. I would not recommend using it. I think being explicit is useful and important. A lot of this is about reproducibility. You don't want to have a configuration change where the default changes for whatever reason, and then suddenly your script no longer works. So if you bake all your settings into your script, then it's going to do the same thing every time. That's a good question. Thank you. Let's keep going. So we've just run a job, which is fantastic. Let's look a little bit more detail at what we did. So I'm not sure if yesterday you touched on the topic of batch scripts. So this is basically a file containing a list of commands that the shell environment runs one after the other on your behalf, so you don't have to sit there typing them. This is really useful for automation. You can get quite sophisticated things done. Back in younger days when I was a radio astronomer postdoc, some colleagues shared a story of someone who was at the Parkes Radio Telescope and was doing follow-up pulsar surveys. So basically when there was a detection of a particular radio astronomy or astrophysical object in the sky, in one particular spectrum, a lot of the radio telescopes would then all point at it and have a look at it to get more detail. And it was a bit of a competition. So different radio telescopes around the world wanted to be the first ones to get the results and publish them. So this particular researcher was like, got the alert, started typing in all the commands, and could only get part of the way through before someone had already published the results. And just like, well, I'm going as fast as I can. How did it happen so quickly? And the answer was scripts. Like someone had already taken all those commands that he was typing, put them in a script and just run the script, and it had done it much faster. So batch scripts are really useful. And it means we don't have to keep typing the same commands over and over again as well, which is really helpful. So the interesting thing about a batch script as opposed to just a normal shell script is that there's a little bit of extra stuff in there. So normally a shell script has just the commands, whereas the Slurm batch script also has these directives in them, which are these comments that start with sbatch. And the scheduler uses the file twice. So when you submit your job to the scheduler, it will look at your script and it will look for these comments to figure out what you're asking for. And so that's kind of like a first pass. It goes, oh, okay, you want 10 nodes for 24 hours. Okay, now I know what you want. I will then go and figure out when that's going to happen. And then when those 10 nodes are available, then it uses the script a second time. It's going to ignore all of those comments and actually run the script and run the commands on those nodes on your behalf. So you've kind of got the one script being used for two purposes. One, to tell the scheduler what it is you want, and the other to tell the scheduler what you want to do once you get the nodes that you want. We recommend putting absolutely everything into the batch script. So don't use your startup login scripts to set up environments. Your batch script should set up the environment, load all the modules you need, set environment variables, so that if you gave that job script to someone who had just logged into for the first time and not touched anything, it would still do the same thing. And that way you have reproducibility. If you're contacting the help desk and saying, help, my job script's not doing what I expected, and you provide the job script, we can run it and it's going to do the same thing for us. If new colleagues get added to your project and you want to share how you're doing your work with them, you can just provide them a copy of the batch script and it will do the same thing for them as it does for you. So it's really important. So we've had a little bit of a look. And we're going to have a look at submitting the monitor.sh in the running jobs tree. So, so currently I'm in the Supercomputing user training job scheduling overview directory. So I'm going to jump out of that. And then I'm going to change directory into the running jobs directory, have an ls to have a look, and we can see this submit monitor.sh. And let's actually have a look at it. So I'm going to use the less command to show the contents of the file, and I want to show the contents of the submit monitor.sh. And what we can see is we have these different parts that we'll be kind of going through, but you can see these directives that are asking the scheduler to say, hey, I'd like some the ability to run some tasks, and I want to run it for a minute. So this is asking for effectively one core. So one core per task, one task per node, one task total, and we're asking it for 1 minute. And it's just going to print out the date. It's going to go into a loop, and every 15 seconds, it's going to print out the name of the node that it's running on. And then when it's done, it's going to print out the date again. I just press Q to get out of that for anyone following along. So let's submit it. So I'm using this sbatch command to submit the job script. Once again, I'm going to use the reservation that we have set up. Once you're using your project properly, you just leave the reservation part out and just have to wait. Oops, no, we're running submit monitor. So that is submitted, and you'll notice when we are submitting here, we are getting our ID provided to us, which can be very useful. So if I now run that SQ command again, I'm just going to do a Control R to search for and just type in SQ, and that'll bring that command back out of my memory, command history. And we can see that that monitor, submit monitor job is now running on node 1009. And if we do an ls, we can actually see our output that's here. And then given we can see that output, I wonder whether that means the job is finished. It has. So I've just run sq-me. The job's no longer showing up, which means it's finished. And we have this slurm.out file. So this is produced at the conclusion of the job. And we can have a look in that one again with the less command. And this is the output from the job. So you can see at the beginning, it output the date. It then showed us that it was indeed running on node 1009. And it did that loop twice, and then it printed the date and time that it finished. So that's the output from our job sitting in this slurm.out file. how can we check what time and resources were used by the first job.sh? So there's a few ways you can do this. If you're quick, I think you can do an S control show job and then the job ID. But this is really for jobs that are active on the system or recently completed. And so you can see here you had a start time and an end time here. But after a while, I believe that you're no longer able to query this. It's only for sort of active jobs. And so if you're looking for more historical information, then there is a command called saccount. And that will print out all the jobs that you've run. I think by default, it runs it for the day. And then if you, all of these Slurm commands are very highly configurable in terms of the columns. And so if you actually look at the manual page, using man for manual, and then the command, which is saccount, you can see if you just scroll down, there is a -o or -- format. And that will sort of, you provide a comment separated list of fields, and you can select from all of these different things about the job. And in there will be sort of start times, end times, and things like that. So you can get a feel for what your job actually did. That was a good question. I hope that helped. Alrighty. So let's kick back up to the slides and keep going. So another important thing to be able to do is to cancel a job. Yes, if you're looking for individual jobs, I believe that is the way to do it. There may be a tool that will let you do it, but off the top of my head, I'm not sure if that's something we have done yet or not. But it's certainly something we're looking into. But currently, you can definitely use the start and end times to calculate your usage. And you can also look at the your Pawsey account balance. So if you run your Pawsey account balance before you run the job, and then after you run the job, you can see the change. But certainly having something where you can just specify a job ID, I think would be really helpful. So again, good questions. So for the cancelling a job, we can come to our examples again. If we do an ls, there's a cancel.sh. So I'm going to try and find where I submitted and submit the cancel.sh. And now, if I'm quick, hopefully I can do an SQ, and so it's running, and I'm going to cancel it. So Slurm cancel 423802, saying I don't want to run that job. I've made a mistake. I've looked at the output that has been produced along the way, and I decided that I really don't want that job running anymore. So now if I look at the queue again, it's no longer there. And if we look at the output, I might use cat this time. So concatenate will print the output of Slurm 43802, because that was the ID of the job. And you can see you've got this error message here. So Slurm has told us that it's cancelled the job in the output, which is helpful. There's also an example there for hitting the time limit. So this one takes a couple of minutes to run. So I might maybe if you want to just use sbatch to run that with or without the -- reservation. and then check back in a couple of minutes and have a look at the output, and you'll see an error message around the fact that it ran out of time. Yeah, the slurm.out is a built-in thing, the format of that, but you can override it. And I think there might be an example on that coming up where you can override the output. So hopefully you should see an error message like that in a couple of minutes if you've submitted that time one. Other errors that you might come across. So if you're a programmer, you have probably come across seg faults. This occurs where you've messed up your math as to which array index to address, or your pointer arithmetic, and so you're trying to access a memory that is not allocated to your program, and your program will die and you'll see one of these seg faults. And so this is the kind of error message you'll see if you have one of these. You can also run out of memory on the node. So this is particularly for programs where the amount of memory it uses might not be determinate. It kind of like depends on the data, and sometimes it just keeps using more and more memory as it tries to run an algorithm to do your processing, and you hit the memory limit, in which case you'll see a message much like this one. So the rule of thumb is if something goes wrong, start looking through the output for things that say error. Errors and warnings are quite useful. So I think I've already shown using scontrol show job ID. And so you just put the ID there, which will give you information about jobs that are currently in the queue running or for a very short amount of time after they're finished. And we also had a look at saccount to list our history of previous jobs. You can specify specific jobs with -J, and you can also select a time window. So from -S for start and -E for end. And that time format is sort of like a date dash time. It can be quite good to kind of, if you're interested in how many jobs you ran in the last month or this quarter, that can be useful. I think by default, it's the jobs that have run since midnight. There's also Ceph, which displays the resource usage of a job in a slightly more human readable way. So we can go Ceph and then the job ID. And so you can see information about what your CPU utilization and efficiency. You can see your wall clock time, so that is a useful way to pick up on your wall time if you don't like doing the arithmetic of the start minus an end time, and your utilization and efficiency of your memory. So there are times where it's really useful to run an interactive session. And so this is usually when you are doing debugging, something's going wrong and you want to figure out why. You can sort of use this interactive session and then just start manually typing the commands of your job script. So you can have a quick look at that as well. So if I just type salec, it's gone and grabbed this access to a node. In particular, we're on node 1086. I suspect by default we're on there with shared permissions, so other people can make use of the node as well. And we've probably just grabbed one core of it. So if you're wanting to reproduce the conditions of a job, all of the things that you specify as directives in the job script, you can specify at the command line. So you can specify a particular petition. You can specify run times, number of cores, and all of those directives. You can just put them as command line arguments to replicate behavior. I'm not sure why this error message is occurring. I think there might be a minor configuration issue with our launching of SALIC, but I don't think it's something we should be worried about here. So now if I do a host name, you can see I am indeed on node 1086. I'm no longer on the Sutonix 03 login node. And so all the commands that I'm typing here are running out on a compute node. And a way to think about this is you kind of, once you've typed your SALIC and you're out on the node, it's almost like you're sitting inside your batch script just after the directives. So then if you want to replicate it, then you just start typing it line by line and sort of until you hit your error to try and get a better idea of what's going on. So I'm going to, you can type exit and press enter, or you can do a control D to get out of that. And that brings us back to the login node. So now we're running back on the login node. I don't recommend running interactively out for your actual work. Like you're literally burning core hours when you are sitting there idle. So I strongly recommend writing job scripts, and then you get reproducible scripts that you know that they'll do the same thing when you run them again, which and it serves as a record of what your job did. So when you're coming back a month later and going, oh, what was this job? Definitely keep a copy of your job script with your output files, so you know how they were created. So yeah, other uses for interactive sessions, if you're compiling up your software, if you're doing some debugging, sometimes maybe you're wanting to tar something up and it's a bit bigger than what you'd want to run on the login node, then it's a way of still doing it interactively, but not putting that extra load on the login node. And you'll notice that I got in pretty quickly there. If you make a larger request, so this SALIC is asking for 100 nodes, you'll see that it just sits there. So it's saying, job queued and waiting for resources. If you log in using a second terminal session, you can actually use the SQ command to get an idea of what your priority is, and sinfo to see how busy things are, to get a feel for when your job's likely to run. If you are requesting an interactive session with more resources and you're having to wait. But again, this is where you can waste a lot of compute time. Like if you think about 100 nodes, which each have 128 cores on them, then that's something like what, 12,000 SUs if you just leave it open, sitting there, not doing anything every hour. So yeah, I highly recommend scripting things out. All right. So I think this might be a good point to have another pause. So maybe we'll take another 5-minute break. Again, I cannot stress enough getting up, moving around, and taking a break from the screen. And if you have any questions, feel free to throw them in the chat, and we can go through them at 1:35 West Australian time, or in 5 minutes. Apologies to those in different time zones. Yeah, so the question is, what is wasting hours? So if we just come back here, so I'm on the login node, right? I'm not being charged for anything. When I do this, I've been granted a job allocation. I am making use of node 1086. It is counting against my allocation. This is probably just counting against one core of my allocation if my assumption about the defaults for SALIC are correct and it is just one core. Worst case, it'll be 128 service units an hour. But if I just leave this for an hour, then I'm going to have consumed an SU. And this is more dangerous if you have, like if we had that 100 node job and we forget to log out, or like you just any time that that prompt is sitting there, even while I'm typing, like I'm just using up allocation and not getting anything for it. So it's not until I'm back out on the login node that I'm no longer consuming time anymore. All right, I'll be back in 3 minutes. Alrighty. So there were a few questions. One was how you can tell which node you're on. So I think hostname is the most portable way of telling. This command's usually available on most systems. And so you can see here, we've got Cytonix 03. The login nodes are called Cytonix dash and then a number. So that means we know we're on a login node. You can see earlier when we were on the compute nodes and we typed hostname, we got an NID and then a number. And so if it starts with NID, that is a compute node that you're on. And I believe the data mover nodes start with a DM and a number. And the shell that we are using and have set up on Cytonix by default will also include the host name in the prompt. So you can see here, we've got our username and the host that we're on in the prompt. And then when we had that interactive session earlier, that changed here, but not every center will do that, which is why I'm telling you about host name, because that's something that is useful if it's not showing up in your prompt. All right. Oh, I think there was another question. What was the other question? Yeah, so you are not charged for anything when you're on the login node. It's only when you're submitting something to the scheduler. And in this case, we're using salloc to submit an interactive job to the scheduler. And then earlier we were using sbatch to submit those batch jobs to the scheduler. All right. So how do we actually write these batch scripts? So I introduced this terminology a little earlier. So a process is a running instance of a program which has its own private space of memory. So a process can be executed as one thread. So if you have a serial process, it just goes through the instructions in the program one by one, and you have a process with one thread. And then there's parallel programming techniques you can use that allow you to have multiple threads running in a process, and they can all share that private memory space. And so the thread is an active thread of execution that is going through and carrying out instructions one after the other in the program. So there are two types of paradigms for doing parallel programming. One is called distributed memory, and this is where you have multiple processes that are running at the same time. So you're running multiple copies of your program as separate processes, and there's a library called MPI that will allow those processes to pass messages to each other. So the first program will hit a point where it has an instruction that tells us to send a message to one of the other processes, and the other process will have a point in its instructions where it will say check for a message from the other process. And then that's how the information and the data moves between processes. And so this is sometimes called message passing. So this is really powerful, the distributed memory and memory passing, because that can occur over a network. So you can have processes running on like thousands of nodes of the supercomputer, and they're all talking to each other using this message passing framework. The threads use a shared memory parallelism. This is where you have one copy of your program running, but within it, it might have multiple threads of execution that are sort of running some of the instructions at the same time. And because they're part of the same process, they share the same memory and can sort of communicate by just directly accessing variables because they're the same variables for each other. A commonly used specification for this is OpenMP. And the only downside of shared memory parallelism is that you can't use it across nodes. So you can use it up to the 128 cores of one node on Cytonix, but that's where you're limited. Whereas with distributed memory parallelism, you have to use these messages to communicate. You can't just directly access variables, but you can scale beyond a node. You can run on thousands of nodes. And so they're the relative pros and cons of both of these. MPI and OpenMP are very robust standards that have been around for a long time and have all the capability you need for doing parallelism. So I would strongly recommend, if you're making a choice of what should I use for parallelism in an HPC environment, I strongly recommend using MPI or OpenMP. I've also touched a little bit on GPU accelerated paradigms. And so this is where you have that graphics processing unit that is there in addition to the central processing unit. And there's lots of different interfaces available for that. For AMD GPUs, there's HIP. For NVIDIA GPUs, there is CUDA. And then there's some of these other paradigms such as OpenMP, OpenACC, and OpenCL can target one or both of those types of GPUs. But it's probably a topic that goes beyond what we're trying to cover today. But it's worth being aware of. So let's have a look at our bash scripts. So here, I think I ran this command earlier, where we're catting the contents of that submit_monitor.sh script. And you can see it's got these different parts to it. The first part here is telling the shell environment, the operating system, what kind of file it is. The hash or exclamation mark symbol here is telling the environment that this is a shell script. So it's a file that contains commands to be interpreted. And the path following that, /bin/bash, is telling it which interpreter you use to interpret the file. So this is a bash script, so it should be use the bash interpreter. The -L is telling it to interpret it as a login script, so as if you'd logged into the system and then run these commands. It's just recommended to always use the -L or a -- login to make sure you're getting the same environment each time. So ignoring for a moment the directives, you then have any legal shell scripting environment for the bash shell. You can put that in here. And so here we're echoing the date, we're doing a loop, we're typing, outputting the host name a few times, and we're outputting the date again. We then have this, the directives. And so it's worth noting these are comments. So as I mentioned, this script will get used twice. The first time the scheduler will just look at the script, it won't run it, it will just look at it when you submit it and say, oh, you've got these directives here, you're asking to run in the work partition for one task with 1 core per task. So you're really asking for 1 core on a node. And you want it for 1 minute. So I'm going to go away and look for a free core that's available for a minute and give you an opportunity to run on that at some point in the future. And then the second time is when that core becomes free, and you go, okay, now that core's free, I'm going to run this script on that core. And so it's going to come in and it's going to go, okay, it's a batch script. I'm going to start running these commands one by one and work its way through it. In terms of the directives and what you're asking for, some common ones are here. There's actually quite a long list, and if you look at the man page for SBatch, you can find a lot of them documented. You can override the job name. By default, it just uses the name of the file that the job script is in, but you can actually customize what that shows up in the SQ. You have your project ID. So which project you want the accounting to count against, the petition you want to run in, and how long you want to run for. And then we have the actual layout of what it is you're asking for in terms of the number of processes you're planning to run, how many processes per node you would like to run, and how many threads per process you're planning to use, and how much memory per node you need. So you want to specify all these for your job script, so that the scheduler knows what it is you're looking for when you submit it. So by default, there is shared mode access, which means if you ask for less than 128 physical cores, so you only ask for, say, 64, then someone also asking for 64 may run on the other half of the node. This can lead to less predictable performance because the node shares some aspects of its hardware architecture. For example, your memory bandwidth, your I/O out to the rest of the network. So if the other job that's running is really using a lot of communication, you might find that your job's taking longer to run. So there are drawbacks to using shared mode access, but it is convenient in that you can potentially, if you have a job that needs 8 cores, then you can just submit a lot of 8-core jobs to the queue, and they will all just pack in and run. If you are using shared node access, we recommend a couple of extra directives. One is end tasks per socket. This is useful if you're using less than half the cores, so 1 socket on the node. And this just forces all of your threads onto that socket, so they're running together on the one processor, which is a good idea. And the other thing to specify is that this -- distribution equals block, block, block. And that is just making sure that your processes are packed together tightly, so they're more likely to be sharing that layer 3 cache that we saw earlier in that chiplet architecture. And again, multiples of 8 work well with the architecture because those little chiplets are in multiples of 8. There's 8 of those chiplets with 8 cores on each processor. If you would prefer not to have other people running on your node, you can ensure that happens by using the -- exclusive directive. This means that your performance is a lot more predictable because you don't have other people running, but it does mean you'll be charged for all 128 cores on the node. We always recommend being explicit in terms of putting all the details in rather than relying on defaults. And it's also worth performing test runs. So don't write your job script and then consume 1 million core hours with your first job, because there's a good chance that something's going to go horribly wrong and you might waste a lot of time. So definitely start with some shorter, smaller test programs until you have a feel for it, and then work your way up to your full production runs. So that's all about how to ask for the shape of what it is you want to use on the supercomputer. Then we get to actually running things. And when it comes to execute your program, you should use the srun command in your batch script. And what srun does is it launches your parallel programs onto all the cores that you have allocated. This is particularly relevant if you have like a job with multiple nodes and you want to launch your MPI parallel program out onto all of the processes of all the nodes. Then you definitely need to use srun. It's also used for launching your threads and getting your threads attached to all the cores correctly. You don't technically need to use it if you have a serial program or if you want to risk it with multi-threaded programs, but we highly recommend always using it because you get more reproducible behavior. You have 2 options for how you run srun. One is you can leave out a lot of these command line options and just run your program, and Slurm will do its best to guess from what you've set here as to what you want the program to do. I recommend being explicit and telling it exactly what you want to do. And so this -n will provide the total number of processes that you're planning to run. The n tasks per node will specify how many processes you're planning on running, and the -c will specify how many threads per process you're planning to run. And then you just run your program. These backslashes are allowing this one command to span multiple lines. And so if you prefer, you can leave them out and just have this as one line in your job script. So here are some examples. Again, I recommend being explicit with the srun and not just relying on it to calculate it. So this is an example of an MPI job with exclusive access. So we've asked for the whole node for a minute, and we're saying would like 256 tasks with 128 tasks per node. And so really what we're asking for here is 2 nodes with 128 processes on each node and 1 core per process. And so you can see here this is 1 node. And so there will be another node that looks exactly the same as this. And you can see there's a P for every process that we just launched. So when we're running hello.x, what srun is doing is it's launching 256 versions of hello.x and putting 1 on every core of these 2 sockets, and it will do it again for the second node. And all of those processes will start running our parallel program. So a process is what we call a program when it's running. So a single instance of a program that's running is a process. So here we'll have the 1 parallel program with the commands in it, and we're running 256 processes or versions of that program. Yes, in this context, a task is a process. Yeah, unfortunately the terminology of Slurm and other things can change quite a bit, and even Slurm at times is not internally consistent, so it can be a little confusing. So we've got 256 versions of this program, of processes, with 1 running on each core here. And so they will communicate using the message passing interface to work collaboratively on a big parallel problem. So this is an example of using OpenMP, which was that shared memory parallelism. So this is using threading. So threads don't pass messages, they all share the same memory. So they can all just look at each other's variables, or look at the variables of the program. And so we have 1 process that is running, and then we have all the threads of that process with a thread running on each core. So for this example, we're saying we have 1 process with 1 process per node, but we have 128 CPUs per task. So we're running with 128 threads. That's what we've asked for. And these are some OpenMP environment variables that specify how we would like those threads placed in what order. And the total number is this environment variable, which is grabbing this value from Slurm. Finally, we have an example that is using both MPI and OpenMP. And so in this example, again, we're using 2 nodes, and we've only shown 1 of those nodes here because they're identical. So we've asked for 4 processes or 4 tasks, 2 tasks or processes per node. You can see them here, 1 and 2. So we've got 1 on each socket. And then we're saying we'd like 64 threads per process. So you can see these 64 threads will belong to this process, and these 64 threads belong to this process. So one of the reasons we would do this is that each socket here, or each processor, has its own memory controller. And so all the cores here accessing memory have the same access time, whereas if these cores were wanting to access the memory running on this processor or managed by this processor, it would take slightly longer for it to go across and request it. So this ensures that all the threads that are running in this process access memory at the same rate, and all the threads running in this process access memory at the same rate. And then to communicate, it's going to use that message passing for the MPI. So this is another example where we're using shared access. So we have 64 tasks or processes per node and also per socket. So we're making sure they're all here and not spread across the two sockets. We're also asking for that block distribution to make sure they're all packed together. And we're only having one thread per process, or one CPU per task. And so we just have one process running per core. This is an example where we only have one process running, one thread, but we need some memory. And so we've asked for more memory, and that's basically locked out these cores. And this one thread is using the memory that would be associated with all these cores. So therefore, only 3/4 of the cores are available for others to use on the node. If you are running on Topaz, or if in the future on phase 2, or you're using Garawala, you may want to make use of the GPUs. This will be particularly relevant if you're doing a machine learning project on Topaz. And there you will need to also request the GPUs to use. So here we can see we've got a --gres equals GPU:1, saying I'd like to use one GPU with my job. And I believe Topaz has up to 2 NVIDIA V100 GPUs per node. So you could, if you wanted both of them, you do a GPU:2. So that was all very exciting. I appreciate that it may be a little foreign if you haven't ever used MPI or OpenMP, but a lot of the parallel codes that are used in HPC do make use of it, which is one of the main reasons we cover it. So we now have an exercise to try running a parallel job. So if you go into the examples directory of the running jobs directory of our user training material, you'll find that there's a hello.c. So this is a C program with a make file, which is the recipe for compiling it. And if you run the make command, it will look at this recipe and run the relevant commands to turn our human readable source code into a machine readable executable to run. And in there's a number of different job scripts that you can pick and choose to try running to see what it does. And once you've run it, you can then have a look at the output files, which will have that out extension. And I think there was that question earlier about renaming your job output files. I believe some of these scripts have that example in them if you go have a look. And so the output might not start with a slurm dash and a number. It might be something else. But I'll give you a couple of minutes to have a look. I see there's a question about batch scripts on Nimbus. There is no scheduler on Nimbus. You have it to yourself, so you can just run to your heart's content. So it's effectively like your login node is your computer. You've got your own instance. You can administer it. You can run things on it, and we rely on oversubscribing, and so there may be other instances running on the same computer to use up the spare cycles when your particular instance isn't doing anything. Not at all. It's more like if you're just interactively on the node writing commands. So you don't have to wait for jobs, you don't have to use SQ, you don't have to use Slurm. You can just log on to the node and log on to your Nimbus instance and run whichever commands you like. So the downside is that you do have to do more of the sysadmin work of setting stuff up. The upside is there is no scheduler. Yeah, and so I think the other thing to take away from Nimbus is that you don't have the option to scale out. So once you have used up the resources of your instance, that's what you get. Whereas on a supercomputer, if you're using the MPI and you're like, well, one node's not enough, you can start running on 2 nodes, you can run on 10 nodes, and you can really scale out across the whole system because of that interconnect that's connecting all the nodes together. So supercomputers are very much built to support that MPI style programming. All right, let's have a look. So I think I just need to cd into the examples directory here. And let's just have a look, which might be of interest if you've never done any C programming before. So we'll do a less hello.c just to see what's in there. And so this is what a OpenMP MPI minimal C example looks like. So if you're a Python programmer, you may be familiar with including Python packages. C is very similar. You can include headers. We have a main function, which is where all C programs start. And what this program is doing is it's first off initializing MPI. So it's telling MPI, hey, I'm an MPI process. There may be others of me, right? So this program, when it's run, if you're using the MPI examples, like you're literally running like potentially like 128, 256 versions of this piece of code. So all of those different versions are going to be going through this, not necessarily exactly at the same time. And so one particular instance, one particular process will come in and initialize this MPI to sort of connect through to the fact that there's other versions of itself running. It finds out how many other versions there are. So that's the COM size, how many other processes are there, and its rank. So of all the other processes, so if there was 128 processes running, am I the first one? Am I the 128th one, 127th one, or 0th one, depending on the indexing? And what is the name of the processor that I'm on? We then create a couple of variables, which is relevant because this is a MPI OpenMP. So we've got through the MPI portion of it, where there's other versions of the program running, and now we have this particular process is using threading within it, right? I'll get back to the question after this. So the threading here, we have this comment, which is telling the pre-compiler the following section between these braces, I would like you to do in parallel using threads. So, and I'd like you to make use of these variables privately. So only So each thread has its own version of these two variables. And within that section, each thread is going to query how many threads there are and which index of the thread it is. And so now so each thread will have its own, hopefully have the same number of threads, but its own index. And then from there, each thread of every process is going to type out hello world from which processor it's running on, what rank it is out of how many processes. I feel like that should be processes rather than processes. And then which thread out of how many threads there are. And then we kill off all our threads as we exit this region. And then we finalize our MPI and say, hey, I'm an MPI process, I'm done. And so that way the MPI implementation will expect that to be called from all the different versions of the process. So that is your 1 minute crash course in C, MPI, and OpenMP. Yeah, don't stress if you haven't picked all of it up, but I feel like a little bit of exposure might be helpful, so you've got an idea of what it's about. Now we want to compile it. So actually, I'll come back to the question. Not necessarily. So the question was, is it optimal to use the maximum number of cores or nodes for a data-driven model? I don't think it really matters on any model. The next section of the slides actually will talk a little bit more about this. You want to use the best configuration to get the most efficient performance possible. And there's lots of different resources on the node that your program might make use of. Like there's the cores and the computational power of the cores, but there's also the memory bandwidth and how much memory you're using, and as well as how much I/O and input/output and access to the file systems you're using. And so if you say, if you hit 8 out of the 128 cores and you're already saturating the memory bandwidth and you're waiting on memory, adding more cores might actually slow things down, because then you've got more cores competing for the available memory. So there can be sweet spots. And we'll see, I'll talk a little bit more about that in the next section. So we have a human readable C file, and we need to compile that up into machine code. So we have our make file, and I will just cut that out so we can have a look at it. And this is just setting up some environment variables, saying we want to use the CC compiler with some flags to make use of OpenMP and use some optimizations. And we want to compile up the hello.x file. And to create the hello.x file, if you've got a .x file, then you need a .c file associated with it. Use the compiler and the flags to compile it up. So basically run this command using the compiler and the flags. And then there's also a command there to clean it up as well. So again, don't stress if you don't follow all of it. It's just a recipe for building things. Oops, that's my habit. So now we can just type make, which will read that recipe in the make file and run the command to compile the code. So we've used the CC compiler with those flags to output a file called hello.x from the human readable.c file. And so if we now do an ls, we should see we have a hello.x file there, which is all compiled up. If I try to run it less on that file, it warns us that it's going to be a binary file. Let's have a look. It's machine code. It's not human readable. But you can see occasional bits of data in there that is relevant. Pressing Q to get out of that. Alrighty. So I think the slides recommended this script. So let's have a look at that one. So again, I'm going to use less to look at job, hybrid, MPI, OpenMP exclusive. So this is where we see the answer to that question. Right here, we're saying we want the output to be the name of the job, I'm assuming that the %x is. we'll see, and with a dot out on the end. And then we're asking for the work partition. We're asking for 4 processes, 2 processes per node, which means we're asking for 2 nodes, 4 divided by 2. And we're wanting 64 cores or threads per process. And we're asking that for a minute. We're setting up our OpenMP threads so they know how many there are to run. And then we're just using srun to run .hello.x. So let's use sbatch with our reservation. And I cannot remember if it was intern or interns. So I'll cheat. I've just done is it Alt-R or Control-R to search for intern, and that's brought this command up that I typed earlier. So I'm going to backspace out that and then type in the new job script name that I want to run. All right. Yes, it does. In fact, the entire reservation may count against your resources, even if you don't use it. I'm less certain of that one. But typically, you won't use reservations outside of training, where your allocation won't matter. Or if there's something very particular that you're doing on the system. But typically, I think we used to use it a little bit for those high priority jobs where people had requests, but since we've implemented the high QoS, I don't think we've really used them that much. No, if you're using Nimbus, you just use it. I think there might be, while your instance is running, it might be counting against your usage. And so you might want to close down your instance when you're done with it. Yeah. I'm not sure if we have some more Nimbus specific training later in the course, Edric.
We're scheduling in a Q&A session for next Thursday, 10 a.m. We're making an announcement in the Slack session soon. So we'll be in touch. The mentors will be in touch with all of the users Nimbus users to help them get up and running. And then once they're in the system, we're decided it'd be interesting to have a Q&A session. They could have a chat with staff and cloud services admin about how to get the best use out of their Nimbus instance, and perhaps some of the workings behind the scenes.
That makes a lot of sense.
Yeah, so I keep your eyes out on the general chat for more info. Thanks, Chris.
I think in terms of the scheduling, you should keep an eye on the chat. When I run Pawsey account balance, I see allocation 50,000. No, so are you running that on your intern account? If you're running it on your actual account associated with your internship, then that would be your allocation for that intern project. If you are running it right now, so if, for example, we did a Pawsey account balance, this is the account balance for this training course this week. And so these COU accounts will probably be cleaned up, deleted, and passwords reset sometime later next week. So definitely think back to what we were doing at the beginning in terms of using SCP to copy things off. You want to do that before the end of the week. So we've currently used 4 SU out of our 50,000 for the week. and that's shared between everybody. So it's really important to understand that your allocation is for everyone in your project. So if I do a -U, you can see we've got 50,000, and then all the users are sharing that 50,000. But yeah, these are good questions. So hopefully our job has run. If I do an SQ --me, oops, me, no, my fingers are failing me. That's looking good. And if I do an LS, you'll remember we had a changed output name, and that %x was indeed the name of the script. So this was the name of the script that replaced the %x in the job script, and so the output ended up as this. So I will let's have a look at it. Actually, I might use less. Oops, no. Yeah, the mouse usage of Linux versus MobiXterm and many others sometimes confuses me. All right, so you can see we've got heaps and heaps of lines of output. So you see there's a lot of hello worlds from processor on 1012. And you can see this is from rank 1. So this is the MPI rank. So this is process 1 out of the 4 processes. And then you've got all the different threads. There's 64 threads running in that one process. And so you can see 0 through to 64 of that first one. And then you can see it's not necessarily in order. This is all running at the same time. So whichever order they happen to hit is the order they happen to come out. And so you can see some of the rank 2s started coming through here, and then it went back to rank 1. And if we scroll down, eventually we'll get to rank 3, and you'll see rank 3 was running on the other node. So these 4 processes with an ES, not an OR, 2 were running on one node, 2 running on the other node. Each one was running on its own socket, and then each of those processes had 64 threads associated with it that were running on each of the cores. I just press Q to get out of this. All right, let me check my chart. We're looking good. Cool. Any questions? Feel free to chip in. I appreciate we're getting towards the end. So we've got about 10 minutes left. So let's get back to the slides and keep moving. All right, so testing job runs. So it's really important to test things. As I mentioned, you don't want to burn like 1 million core hours accidentally or service units accidentally. So it's always important to make sure that the program you're running is doing what you expect it to before it starts consuming large amounts of time. And the other thing is that we also want to make sure that we are making optimal use of the resources. Let's say you had a 1 million SU allocation. If you can make your code run 10% faster, that's an extra 100,000 SU that you can spend on doing other science. Performance is important. It means you can get more science done with the resources that you can get allocated to you. And more importantly, if everyone is making sure they're making efficient use of the system, then the supercomputer as a whole can have more impact on science, and we can have, I guess, a better impact on society at large. So running performant code at scale is really important. Another reason to run test jobs is if you're preparing a merit allocation. So merit allocations are very competitive, and one of the things you want to not do in your allocation is say, I've got a very important science project. I'd like 1 million core hours for it, please. Because it doesn't make a very good justification for why you need that 1 million core hours. What a good application will look like is, I'd like an allocation to do this science, I've already logged on to the system using sort of these intern projects, or you can also get sort of short benchmarking projects to get on there and do this kind of work. I've already logged onto the system. I've already installed my software and confirmed it works. I have run some basic benchmarks of my software that gives, and I can provide graphs of the scaling of that software. So I am confident that the amount of time that I'm asking for is a good use of this system. And based on those benchmarks, I believe in order to run my science, I need to run 100 runs of this particular workflow at this scale, a couple of hundred runs of this particular workflow at this different scale. And when I add all that together, in order to do this work that I've laid out, I need 2,500,000 SU or 5,000 SU or something like that. And that makes a much more competitive request for why it is you need the time. And it gives the reviewers confidence that you know what you're doing and have adequately thought through what you're planning to do. So for smaller scaling tests that will fit, definitely use the debug petition because you won't have to wait for your results because they should be relatively free. So for that first use case, running a test job for the first time, your goal is to make sure the job is doing what you think. So you want to check that what you're asking for is what you're getting. And you can do that potentially by, instead of S-running your program, you could S-run that hello.x and check that the number of processes and threads are what you're expecting. If you are using an MPI or OpenMP program, that can be a great way to quickly check that things are landing and starting running where you're expecting them to. You can also do things like, say you were planning to run a weather modeling code that was going to simulate the climate for a number of months, and that was going to take sort of several 24-hour jobs. You say, okay, well, instead of simulating the climate for a couple of months, I'll simulate the climate for a couple of minutes and just get a couple of iterations in. So, and then stop. And so I'll run that test job. It won't use up much of my allocation, but I can verify that the output that I'm getting is what I'm expecting. It's running correctly. And then once you've verified that, then you're fine to then change your input parameters, run it for the full 3-month simulation, and run that over a number of job scripts. So in terms of optimizing your resource requests, I touched on this a little earlier. One thing to think about is the time. So this is less important in terms of the efficiency of your allocation usage. This is more of how long you have to wait in the queue. If your runtime is shorter that you're asking for, it's more likely there's going to be a gap for you that the scheduler can fit you into. So you don't want to always just put in the maximum all time. You want to have a sense of, okay, this job typically takes 6 to 8 hours. It'll be very unlikely to take more than 10 hours. So I'm going to ask for 10 hours. So you want to have it as low as you can while being confident that your job's actually going to finish and not get cut off. In terms of the memory requirements, if you're running exclusively, you don't really need to worry about it because you've got the amount of memory that there is on the node. If you are using that shared access, potentially you can start with the default amount, which is a modest portion of the memory. And then if you run out of memory, then start increasing it until you get a sense of what is the memory footprint that your program requires in order to successfully run. And I think the more important thing is the size of your job in terms of how many cores you're using. I talked a little bit earlier about how it's possible that your most efficient usage is not actually using all the cores. It might be, if you are limited by memory bandwidth or other things, it might be more efficient to run with still using the node exclusively, but using a portion of the cores because that is the best performance you can get out of that whole node. So you still have to pay for the whole node because you're using all the memory bandwidth, but at least you're getting the best, most efficient use of that node by running on the right number of cores. And you do that by testing. And I recommend testing in multiples of 8 due to that layer 3 chiplet architecture. So try 8 cores, try 16 cores, try 32 cores, 64, 128, and just time how long it takes. Use the fastest one. Likewise for the scaling. So if you're then starting to look at, okay, well, how many, I've got a parallel program. I could run it on 4 nodes. I could run it on 8 nodes. I could run it on 16 nodes. What size do I pick? Again, you do these small benchmarks to time your performance and see how you go. So this is an example of a molecular dynamics simulation in a water box using lamps. And we are comparing it to a reference run of 24 processes on 1 node. And then we're increasing the number of processes. So scaling up across the calls on multiple nodes and looking at the runtime. Now, if you just graph the relative runtime like this, it can be difficult to see what's going on because you kind of have this exponential curve. And you can see as we're adding more processes, the time it takes to run is dropping. But if we sort of switch to a more logarithmic scale, looking at the relative total cost, you can see that relative to the first one, as you're increasing the number of processes, the cost is increasing. And there's actually a sweet spot here, right? So if you're running at scale, you either want to run less than 200 processes or run at 400 processes, right? But it might be that you look at it and say, well, actually, that's still going to take too long. I'm okay with losing some of the efficiency of my work because I just need to get it run quickly enough. And so it might be that you're willing to move some way up here to sort of get some performance gains, albeit at using your allocation a little less efficiently. And so making graphs like this and understanding, okay, what is my efficiency of using my allocation versus how quickly is it going, and what is it costing me to get things quicker? And often there are these sweet spots where it's a case of, okay, this is something that will get me my results quickly, but not cost an exorbitant amount of service units relative to some of the other options. So in terms of scaling, it's very similar to sort of creating these graphs, but it's useful to understand the 2 types of scaling. One is called weak scaling. So that is where you increase the problem size as you increase the core count. So if we go back to that, that's a good question. I'll get to it in a minute. If we go back to the weather modeling example, if we took the one weather model that we wanted to run and just increase the core count, that's measuring the strong scaling. And what you'll find is that as you start increasing the number of cores, the communication will become a bigger and bigger portion of the processing. And so after a point, it'll actually start taking slower. And so you hit a point where you're no longer getting benefit from adding more cores. Weak scaling is where we're increasing the problem size. So when we double the core count, we might double the size of our domain that we're simulating. And so this tends to scale better and longer. But then you need to look at, well, what is the scale of the problem that we need to run? And that should usually come back to the actual science. So for example, if you're simulating turbulence in a fluid, depending on the scale of the turbulence, there might be a particular resolution that you need to fully resolve that turbulence. And there might be a particular scale of the domain that you're looking to simulate. Maybe you're simulating a jet engine or something, and you need like a sufficient portion of the jet engine to know that you're capturing all of the physics that you're looking to have in that simulation. So in terms of the measuring the scaling, the things that we're interested in is the speed up. And so how much faster is it running as we're adding more cores? And then the efficiency. So how efficient is that speed up? If we're throwing double the number of cores at it, are we getting double the number of speed up, either twice the speed up, or are we getting like 1.8 the speed up? So there's a bit of a cost involved in getting it faster. So to come to the question, if the unit cost is CPUs times hours, then how does parallelism cost anything? It doesn't. So you are indeed correct that you will be charged the same for one CPU for 128 hours versus 128 CPUs for 1 hour. The reason you do parallelism is that you get your results in an hour as opposed to 128 hours. So the motivation for using parallelism is to get results faster. And ultimately, this also comes back to when do you need a supercomputer? And if you have something where you can get the results on a laptop in a day, you don't want to be using a supercomputer because you're going to probably have to wait that day to get through the scheduler to get on there and actually get it run. You want to use a supercomputer where you've got something. Like I had my honors actually. I realized that I was doing some benchmarking of GPU bandwidth, transferring data to and from the GPU, and I looked at how many tests I had to run and how long that would take on my GPU workstation, and it came out to something like 5 months, and I had about 6 weeks left to do my final write-up. So there for me, parallelism was awesome because luckily my supervisor had recently put in a new GPU computing lab, and so we had something like 12 workstations with GPUs in them. And so when they weren't being used of an evening, I would run my benchmarking code on all the GPUs of all the computers in the lab and got my 5 months worth of benchmarking done in a couple of weeks, and managed to finish my write-up in time to get my honors finished, which was amazing. So the motivating factor towards parallelism is getting your results faster. The cost is more about if you want to get time on a supercomputer, you need to have an allocation, and they're quite difficult to get, and you want to get the best value out of that allocation. So you want to run things really efficiently. You want to minimize the amount that you're paying. And so I guess coming back to this, it comes back to the inefficiency from communication. This relative total cost is not just one, right? It's costing us more to go parallel. So as we're using parallelism, there's communication, which also takes time, and therefore it's becoming less efficient as we go more parallel. And then what is the point where that is useful? And you'll find with these scaling graphs, there's points where up to a point you're pretty close to one, and then you'll find suddenly you'll just taper off. And so using parallelism beyond that point is really starting to cost you a lot of core hours to not actually get much more done. And it's different for every code. So that's why it's really important to benchmark and have an understanding of the parallelism in your code to figure out the best configuration. If you didn't, so why would you ever choose one CPU for 128 hours instead of 128 CPUs for 1 hour? Well, for starters, 128 hours is a week. So if I was having something that was taking a week to run on my laptop, I'd probably just run it on my laptop, to be honest. It's not that big of a, like, well, you've got to get scheduling, moving stuff to the supercomputer. It's a lot of effort for that, getting it down to an hour. But I guess another example would be, I was helping a researcher who was doing genomic studies, and they were looking at multi-order collections of genes. So trying to determine which genes were tied to, I think it was organ failure of people with diabetes, because there were interventions that I guess had side effects, and so you only really wanted to take them. But if you did, then you're a lot less likelihood of your organs failing. So like sometimes the side effects are worth it, but if you know from your genetics whether or not you're more likely to have that, then that can help just sort of make that decision. And her workflow again, I think was months, and so she could have just run it for months on a laptop and got a result like later in the year. But we spent a week implementing MPI in the code so that multiple instances of the program could run and they could communicate relevant information about the genes using the message passing to the various versions of the program running. And I think it took a few hours to run. There was a slight overhead cost in terms of the core hours. So I don't think it was, there was some communication overhead, but in that particular instance for that particular code, it was very low because the program only needed to share information on genes fairly irregularly and do most of it just focusing on the individual genes that they're working on, and then just check in with neighbors every now and again to see how they're going with the genes they were working on. Yeah, so yeah, 4,096 cores for an hour, runs quicker. Yeah, no, the overhead cost is for the oh, hang on, sorry. Yeah, you've put hours in there twice, which is making it a little confusing. So advantages of 4,000 cores for an hour means that it runs quicker and there is an overhead because they're communicating. So the overhead's with the runs quicker. So the advantage of running one CPU for 4,096 hours is there is no overhead, but you are waiting a very long time to get your results. And so it's less about these endpoints and more about the slope in between them and knowing where on that slope you're happy to sit for your particular code. So I appreciate that I've gone over time by 10 minutes. So this is another, I guess, example of these scaling graphs showing the ideal scaling and the increasing cost of communication as we're scaling up. So it's not following this dotted line where we're losing performance. But that brings me, I guess, to the end of this section. To talk briefly about getting help. We have very extensive user support documentation. So I thoroughly encourage you to go and have a look at the documentation. As I mentioned, everything I've covered today, there's videos by my colleague Marco in our Pawsey YouTube channel. You can get to that from that training material. If you just click on the play button next to the slides, it's there. And you'll get his take on it, which he might describe things a little bit differently to me, which might be helpful. So if any of the sections you're feeling a bit fuzzy on, feel free to go back and have a look, particularly if it's relevant to your particular intern project. And if you get stuck, I know the interns have some chat channels that they can sort of help each other with, and I think that's really positive, and networking with your peers is a great way to go. If you can't get a solution there, you can always put in a service desk ticket. And if you do, there's things that can be helpful to provide, such as which resource you're on, so on Cytonics, Nimbus, Topaz. If there's an error message, always copy paste it, include it. It will be so much faster for us to figure out what's going wrong. The location of any files you have, like job scripts, job IDs if you're having trouble with the job, or your username if it's login issues. And as I said before, you never need to provide your password. So I think that brings me to the end, although I'm happy to hang around for a little while and answer more questions if anyone has them. Yeah, no, thank you all for sticking around and listening. I really appreciate it, and thank you for asking so many questions. I think in a virtual training environment, it actually really adds a lot. So thank you for being involved and participating. I really appreciate it. Did you have anything you wanted to add, Edric or Emily?
Yeah, no, can you hear me okay?
Yes.
Yes. No, I think from us, we just wanted to say thanks to you, Chris, for taking time out of your day to talk to all our interns. And it was really great to see so much engagement from everyone in the chat. It's nice to see everyone participating and really making the most out of this training.
Yeah, it was awesome to see. And it's a lot to learn in a day, but I think it's just really important to have some context, when you start your project, so you can actually start identifying, like what is important to you. If you don't know the language, you don't know the questions to ask. So I hope this is a really good start for growing this.
Yeah, definitely. I think it's definitely challenging, because I know a lot of the researchers attending our training often have a wide variety of expertise, and you're kind of at different points in your journey of learning how to do computational research, from complete novices to people that have sort of had a lot of exposure to it. So I think an important thing to take away is that as long as you're moving forward, that's the main thing. And there's always time to come back and reabsorb things if you need to.
Yeah, well put, Chris. Thanks for the workshop today. It's a long session to be chairing by yourself, but yeah, it seems like it's gone really well. So thanks.
Cool. Well, I'll stay online in case there's any final questions, but otherwise, thank you all.